Hello there, and welcome to this quiet space where time moves slowly and the Earth's deep history is allowed to unfold at its own pace. Tonight we're traveling back, not just centuries or millennia, but millions of years, to a moment when the world beneath our feet looked profoundly different from anything we might recognize today. This is the story of the Mediterranean Sea when it wasn't a sea at all, a period geologists call the Messinian Salinity Crisis, an episode that lasted roughly 400,000 years, beginning nearly 6 million years ago. It's a name that appears in textbooks, mentioned briefly between discussions of plate tectonics and ancient climate. But few people pause to consider what it actually meant. What would you see if you could stand at the edge of that emptied basin? What would the air taste like? How would it feel to look down into a chasm where water had been, where kilometers of depth now lay exposed or filled with brine so concentrated that almost nothing could survive in it? We're not here to rush through this story or to sensationalize what happened. We're here to let it breathe, to understand how a sea that should not exist in the first place became even more improbable by nearly vanishing, to trace the slow tectonic forces that closed ancient gateways, the patient accumulation of salt layer by layer, and the sudden catastrophic return of water that ended the crisis in less time than it takes for a human lifetime to pass. Before we begin, I'd like to know where you are right now as you're listening to this. What part of the world holds you tonight? It's a curious thing, isn't it? We're exploring a time when continents were still colliding, when the map itself was being rewritten by forces operating on timescales we can barely comprehend. And yet here we are, separated by miles and minutes, quietly sharing this moment together. If this kind of slow, reflective exploration is what brings you peace, I'd be grateful if you considered subscribing or leaving a like. It helps this small signal reach other minds that find comfort in deep time and patient storytelling. No pressure, of course, just an invitation. So settle in, let your breathing slow, let the questions drift in gently. We're going to look at what happens when a sea begins to disappear, grain by grain, year by year, across a span of time so vast that the crisis itself becomes a kind of patience. The Mediterranean Sea, as it exists today, is not a stable body of water. It sits in a basin shaped by the collision of continents, bordered by Europe to the north and Africa to the south. It stretches from the narrow Strait of Gibraltar in the west to the shallow coastal shelves of the eastern Levant. It holds roughly 3.7 million cubic kilometers of water. It supports ecosystems, trade routes, entire civilizations built along its shores. But beneath this appearance of permanence lies a fundamental imbalance. The Mediterranean loses more water than it receives. Evaporation constantly pulls moisture into the atmosphere at a rate that exceeds the volume delivered by rainfall and rivers flowing from the surrounding continents. This is not a temporary condition. It is an inherent characteristic of the basin's geography and climate. The sun beats down, the air is warm and dry in summer. Water molecules lift away from the surface and disperse. Rivers like the Nile, the Rhone and the Po contribute fresh water, but not nearly enough to compensate for what is lost. Without intervention, the Mediterranean would shrink. If the connection to the Atlantic Ocean were severed today, the sea level would drop at a rate of approximately half a metre every year. That is not a gradual decline spread across geological ages. That is a measurable, almost immediate response to isolation. In 2,000 years, without Atlantic inflow, the basin would lose a kilometre of depth. In 10,000 years, much of the seafloor would be exposed. But the Mediterranean does not shrink, because water arrives constantly from the Atlantic through the Strait of Gibraltar. This narrow passage, roughly 14 kilometres wide at its narrowest point, serves as a lifeline. Atlantic water flows in along the surface, slightly less salty and cooler than the Mediterranean water it replaces. At depth, denser, saltier Mediterranean water flows outward into the Atlantic, maintaining a circulation that stabilizes the basin. This exchange is not optional. It is a requirement for the sea's existence. The system is balanced, but only just. The Mediterranean occupies what geologists sometimes describe as a knife edge. A small reduction in the width of the strait, a minor change in the depth of the sill that separates the Atlantic from the Mediterranean basin, and the entire equilibrium begins to shift. The basin becomes vulnerable. not in a distant theoretical sense, but in a way that can unfold within tens or hundreds of thousands of years. This vulnerability is not new. It has always been there, written into the basin's geometry. The Mediterranean exists because tectonic forces created it, carving out a depression as the African and Eurasian plates converged over millions of years. But those same tectonic forces that created the basin also have the capacity to isolate it. The connection to the Atlantic is not guaranteed by any law of nature. It is contingent on the precise arrangement of land masses, the height of thresholds, the depth of channels. For most of the Mediterranean's history, this balance has held. Water has continued to flow in from the Atlantic. Sea level has remained stable. Marine life has thrived in conditions that, while occasionally stressful due to higher salinity compared to the open ocean, have remained broadly hospitable. But the basin's stability depends entirely on the continued integrity of its connection to the Atlantic. Remove that connection, and everything changes. The Messinian salinity crisis is what happens when the knife edge tips. It is the story of what occurs when the Atlantic inflow slows, falters, and eventually stops. It is not a hypothetical scenario. It is an event that actually occurred beginning roughly 5.97 million years ago and lasting for approximately 400,000 years. During that time, the Mediterranean transformed. It became something other than a sea. Whether it became a desert, a series of hypersaline lakes, or a deep brine pool remains a subject of ongoing scientific debate. But what is certain is that the transformation was driven by the same fundamental imbalance that defines the basin today. Understanding the crisis requires understanding this precondition. The Mediterranean is not like the Atlantic or the Pacific, vast and open, connected to the global ocean circulation in multiple ways, buffered by sheer volume against rapid change. The Mediterranean is small, enclosed, dependent. Its existence is conditional. It survives because a single narrow strait remains open. That fragility is the key to everything that follows. The African and Eurasian continental plates have been moving toward each other for tens of millions of years. This is not a sudden event. It is a process so slow that no human lifetime, no sequence of human lifetimes, could register the motion directly. The convergence occurs at rates measured in centimeters per year. Yet over geological time, centimeters accumulate into hundreds of kilometers. Continents collide. Mountain ranges rise, seaways open and close. The map of the Earth is rewritten. The Mediterranean basin exists because of this collision. As Africa drifted northward, the Tethys Ocean, a vast ancient seaway that once separated the supercontinents, gradually closed. The Mediterranean is a remnant of that ocean, a fragment of deep water trapped between converging land masses. But the same tectonic forces that created the basin also shaped the connections that allowed it to remain filled. Before the late Miocene, the Mediterranean was not connected to the Atlantic through the Strait of Gibraltar as it is today. Instead, two major marine corridors linked the basin to the Atlantic Ocean. These were the Betic Corridor, which stretched across what is now southern Spain, and the Riphean Corridor, which crossed northern Morocco. Both corridors were substantial seaways, wide enough and deep enough to allow significant water exchange between the Mediterranean and the Atlantic. These gateways were not static. They existed within a tectonically active region known as the Gibraltar Arc, where the ongoing collision between Africa and Eurasia generated intense geological stresses. The crust in this region was being compressed, folded, and uplifted. Over time, the corridors began to narrow, the seafloor rose, the passages became shallower. Water flow became more restricted. The Betic Corridor appears to have closed first. Geological evidence suggests that tectonic uplift in the eastern Betics, driven by the compressional forces of the converging plates, propagated westward. The corridor that had once allowed free exchange between the Mediterranean and Atlantic began to constrict. Eventually, it sealed entirely, likely during the latest Tortonian or earliest Messinian stages of the late Miocene, roughly between 6 and 6.5 million years ago. The Riphean Corridor followed a similar trajectory. Uplift rates in northern Morocco increased as the tectonic stresses intensified. The seafloor rose. The water column above the sill connecting the Mediterranean to the Atlantic shrank. The corridor that had served as a secondary pathway for water exchange began to fail. By the late Tortonian to early Mycenaean, both the Betic and Riphaean corridors had effectively closed. The Mediterranean's connection to the Atlantic had been reduced to a single, much narrower passage, the nascent Strait of Gibraltar. This was a profound shift in the basin's hydrological geometry. With two major gateways sealed, the entire Mediterranean became dependent on one connection. The strait was not as wide or as deep as the earlier corridors. The volume of water that could flow through it was limited by the cross-sectional area of the passage and the depth of the sill at its base. Any further tectonic activity that raised the sill or narrowed the strait would immediately affect the basin's ability to maintain equilibrium. The closure of the Betic and Riphaean corridors did not cause the Mycenaean salinity crisis directly. The Mediterranean did not dry out the moment those gateways sealed, but it created the necessary precondition. The basin's fate was now tied to the stability of a single choke point. The system that had been buffered by multiple connections became fragile, vulnerable to any additional restriction. Tectonic forces continued to operate. The African plate continued its slow northward push. The Gibraltar Arc continued to experience compression and uplift. The strait that remained open was itself subject to the same geological processes that had closed the earlier corridors. The question was not whether further restriction would occur, but when and to what degree. The tectonic closure of the Betic and Riphaean corridors represents the first stage in a cascade of events that would eventually lead to the crisis. It was a gradual process, occurring over hundreds of thousands of years. The uplift did not happen overnight. The seaways did not vanish in a single earthquake or volcanic eruption, but the cumulative effect was irreversible. Two major connections between the Mediterranean and the Atlantic were severed. The basin's hydrological lifeline was reduced to a single thread. Understanding this tectonic geometry is essential to understanding the crisis itself. The Mycenaean salinity crisis was not caused by a change in climate, though climate played a role in its timing. It was not caused by an asteroid impact or a volcanic catastrophe. It was caused by the slow, patient work of plate tectonics, the same forces that built the Alps, the Atlas Mountains, and the complex fold and thrust belts that define the Mediterranean's northern and southern margins. The Earth was reshaping itself, and in doing so, it set the stage for one of the most extreme hydrological events in recent geological history. With the Betic and Riphaean corridors sealed, the Strait of Gibraltar became the sole passage through which Atlantic water could enter the Mediterranean. This was not yet the Strait of Gibraltar as it exists today. The modern strait is a product of more recent tectonic activity and erosion. During the late Miocene, the connection was likely different in its precise dimensions, its depth, its width, but it served the same critical function. It was the only route for water exchange between the Mediterranean basin and the global ocean. The closure of the earlier corridors had reduced the total capacity for inflow. With only one gateway remaining, the volume of water entering the Mediterranean each year was constrained by the physical dimensions of that gateway. The cross-sectional area of the strait, the velocity of the current flowing through it, and the depth of water above the sill all determined how much Atlantic water could reach the basin. Any change to these parameters would directly affect the Mediterranean's ability to offset its evaporative losses. Tectonic activity in the Gibraltar Arc did not stop once the Betic and Riphaean corridors closed. The African and Eurasian plates continued to converge. Compressional stresses continued to drive uplift across the region. The Gibraltar Passage itself was subject to these forces. The seafloor beneath the strait was rising. The sill, the submerged ridge that forms the threshold between the Atlantic and Mediterranean basins, was being pushed upward by the ongoing collision of continents. As the sill rose, the water column above it became shallower. This had immediate hydrological consequences. The flow of water through the strait is governed in part by the depth available for that flow. A shallower sill means less water can pass through at any given time. The current slows. The volume of inflow decreases. The Mediterranean begins to receive less Atlantic water than it needs to maintain equilibrium. The uplift required to seal a seaway entirely is substantial. Ocean currents exert powerful erosional forces, particularly in narrow passages where water accelerates due to constriction. For the tectonic uplift to overcome these forces and effectively block the connection, the rate of rise had to exceed the rate at which erosion could deepen the channel. In the case of the Gibraltar region, the tectonic stresses were sufficient to achieve this. The sill continued to rise despite the erosional resistance of the currents flowing across it. The timing of the final restriction is difficult to pinpoint with absolute precision. Geological records indicate that the closure likely occurred in stages. There may have been periods when the connection was severely restricted but not completely severed, followed by intervals when the flow resumed, only to be restricted again. This cyclical pattern is suggested by the sedimentary record, which shows evidence of repeated changes in water chemistry and salinity within the Mediterranean during the lead-up to the full crisis. By approximately 5.97 million years ago, the restriction had become severe enough to trigger the onset of the Messinian salinity crisis. The exact mechanism of this final closure remains debated. Some evidence suggests that the sill rose high enough to block the inflow of Atlantic surface water, while still allowing denser Mediterranean deep water to flow outward. This would create a situation where the basin retained its water volume initially, but began to experience changes in circulation and salinity as the surface exchange was cut off. Other evidence points to a more abrupt closure, where both inflow and outflow ceased nearly simultaneously, leading to rapid changes in the basin's hydrological state. The reality may lie somewhere between these scenarios, with the closure occurring over a period of several thousand years, progressing from partial restriction to near total isolation. What is clear from the geological record is that once the Atlantic inflow was sufficiently reduced, the Mediterranean's evaporative deficit could no longer be compensated. The basin began to lose water. Sea level began to drop. Salinity began to rise. The chemistry of the water began to shift as the concentration of dissolved salts increased. Marine ecosystems that had thrived under stable conditions began to experience stress. The closure of the gates was not a dramatic event visible to any observer standing on the shores of the Mediterranean. There was no sudden draining, no catastrophic collapse. The restriction occurred slowly, driven by tectonic forces operating at rates of millimeters per year, but the cumulative effect was transformative. A sea that had existed for millions of years, sustained by its connection to the Atlantic, was now cut off. The preconditions for the crisis had been established by the closure of the Betic and Riffian corridors. The crisis itself began when the last remaining gateway, the Strait of Gibraltar, was constricted to the point where inflow could no longer balance evaporation. The gates had closed, the Mediterranean was isolated, and the transformation had begun. The closure of the gateways created the necessary condition for the Mediterranean's transformation, but it was not the only factor that determined when the crisis would begin. Tectonic forces set the stage by restricting the connection to the Atlantic, but the precise timing of the crisis was influenced by global climate processes operating on different timescales. The Earth's climate during the late Miocene was not static. It fluctuated in response to changes in the planet's orbit and axial tilt, patterns that affected the distribution of solar radiation and, consequently, global temperatures and sea levels. One of the key climate cycles that influenced the Mediterranean during this period was the eccentricity cycle, a variation in the shape of Earth's orbit around the Sun that occurs over roughly 400,000 years. When Earth's orbit is more elliptical, the planet experiences greater differences in the amount of solar energy received at different times of the year. When the orbit is more circular, these differences are smaller. The eccentricity cycle affects global climate by modulating seasonal extremes, which in turn influence ice sheet growth, ocean temperatures, and sea level. Around the time of the Messinian salinity crisis, Earth was moving through a phase of the eccentricity cycle that coincided with the tectonic restriction of the Mediterranean's connection to the Atlantic. This alignment was not coincidental in the sense of being causally linked, but it was consequential. The climate cycle acted as a modulator, amplifying the effects of the tectonic closure by introducing additional stress on the already restricted water exchange. Global sea level during the late Miocene was also subject to fluctuations driven by glaciostatic processes. These are changes in sea level caused by the growth and melting of ice sheets, primarily in the polar regions. When ice sheets expand, water is removed from the ocean and stored on land in the form of ice. Global sea level falls. When ice sheets melt, water returns to the ocean and sea level rises. The amplitude of these fluctuations during the late Miocene was not as large as those that would occur during the later Pleistocene ice ages, but they were still significant. Approximately 6.13 million years ago, global sea level began to fall due to the expansion of ice sheets in the polar regions. The amplitude of these drops was around 10 meters. This may not seem like a large change compared to the depth of the ocean, but for a restricted seaway like the Strait of Gibraltar, even a modest drop in sea level has significant consequences. The sill connecting the Atlantic to the Mediterranean was already shallow due to tectonic uplift. A 10-meter drop in global sea level would reduce the water column above the sill even further, decreasing the volume of Atlantic water that could flow into the basin. The effect was cumulative. Tectonic uplift had raised the sill. Climate-driven sea level fall had reduced the water depth above it. Together, these factors throttled the connection between the Atlantic and the Mediterranean. The inflow of Atlantic water decreased. The Mediterranean's evaporative deficit, which had always existed, now became a destabilizing force. Around 526 million years ago, close to the boundary between the Miocene and Pliocene epochs, a particularly large glacier-static sea level drop occurred. This event lowered global sea level by approximately 30 meters. For the already restricted Strait of Gibraltar, this drop may have been enough to sever the connection entirely, or at least reduce it to the point where inflow was negligible. The timing of this event correlates closely with key phases of salt deposition within the Mediterranean, suggesting that the sea level drop acted as a trigger for the most intense periods of evaporation and salt accumulation. The correlation between sea level changes and the phases of the Messinian salinity crisis is supported by analysis of benthic oxygen isotope records. These records, derived from the shells of organisms that lived on the seafloor, provide a proxy for ice volume and, by extension, global sea level. The isotope ratios preserved in these shells show that the major phases of salt deposition within the Mediterranean coincide with peaks in global ice volume when sea level was at its lowest. This does not mean that climate change caused the Messinian salinity crisis in the way that tectonic closure did. The fundamental cause was tectonic, the restriction and eventual closure of the gateways connecting the Mediterranean to the Atlantic. But the timing of the crisis, the specific moments when the basin shifted from one hydrological state to another, was determined by the interaction between tectonic restriction and climate-driven sea level change. The Mediterranean existed on a knife edge. The tectonic restriction had made it vulnerable. The climate cycles provided the final push. Together, they created a situation where a stable marine environment could tip into crisis within a relatively short span of geological time. The basin that had been sustained by Atlantic inflow for millions of years was now isolated, or nearly so. Evaporation continued at its relentless pace. Water level began to drop. Salinity began to rise. The crisis had begun. The moment Atlantic inflow ceased, or was reduced to a trickle insufficient to offset evaporation, the Mediterranean entered a new hydrological state. The transition was not instantaneous in human terms, but in geological terms, it was rapid. Within a few thousand years, the basin's water balance shifted from stable to catastrophically imbalanced. The sea began to lose volume. Evaporation does not stop. It is driven by solar radiation, air temperature, and humidity, factors that operate independently of whether water is being replenished. The Mediterranean, with its warm climate and dry summers, has always experienced high evaporation rates. Under normal conditions, this loss is compensated by Atlantic inflow, and, to a much smaller degree, by freshwater input from rivers. But once the Atlantic connection failed, there was no compensation. The water that evaporated from the surface was gone. It rose into the atmosphere, dispersed across the globe as precipitation. It did not return to the basin. The rate of water loss was approximately 0.5 meter of sea level per year. This figure represents the net deficit, the difference between evaporation and the minimal freshwater input from continental runoff. 0.5 meter per year is a measurable, almost immediate response. In a human lifetime, the sea level would drop by 20 to 30 meters. In 1,000 years, it would drop by 500 meters. In 10,000 years, the basin would lose 5 kilometers of depth, which is more than the actual depth of most of the Mediterranean. The calculation is somewhat simplified, because as the sea level drops, the surface area of the basin also decreases, which reduces the total volume of water evaporated each year. But the fundamental point remains. Without Atlantic inflow, the Mediterranean was losing water quickly. The initial phase of the crisis, beginning around 5.97 million years ago, did not immediately result in massive salt deposition across the entire basin. Instead, The evidence suggests that the first response was a reorganization of the basin's internal circulation. Analysis of the chlorine-stable isotope composition of salt deposits indicates that the early phase, lasting approximately 35,000 years, was characterized by halite deposition primarily in the eastern Mediterranean. This geographic restriction suggests that the western and eastern parts of the basin were not uniformly affected during the initial stages of the crisis. The reason for this asymmetry lies in the internal geography of the Mediterranean. The basin is not a single, uniform depression. It is divided by the Sicily Sill, a submerged ridge that separates the western Mediterranean from the eastern Mediterranean. Under normal marine conditions, water flows freely across this sill, maintaining similar sea levels and salinity on both sides. But once the Atlantic connection was restricted, the Sicily Sill began to act as a secondary barrier. If the initial restriction blocked the outflow of deep, highly saline Mediterranean water to the Atlantic while still allowing some limited inflow of surface water, the basin would have remained largely brine-filled, but with changes in its internal circulation. The eastern Mediterranean, which is deeper and more isolated from the Atlantic, would have begun to experience increased salinity first. Dense, salty water would have accumulated in the deep basins of the east, while the western basin, closer to the Atlantic connection and shallower on average, retained more normal conditions for a longer period. During this initial phase, the Mediterranean was not yet a dramatically different landscape. It was still a sea, still filled with water, still recognizable as a marine environment. But the water chemistry was changing. Salinity was rising, particularly in the deep eastern basins. Marine organisms that were adapted to normal seawater conditions began to experience stress. Some species could tolerate the increased salinity, others could not. The ecosystem began to shift. The salt that precipitated during this phase accumulated in the deepest parts of the eastern Mediterranean. Halite, the mineral form of sodium chloride, begins to crystallize when seawater is concentrated to about 10 times its normal salinity. As water evaporated and was not replaced, the concentration of dissolved salts in the remaining water increased until it reached the point where halite could no longer remain dissolved. Crystals formed and settled to the seafloor, slowly accumulating into layers that would eventually become part of the massive evaporite deposits that define the Messinian salinity crisis. This was not a desert. This was not yet the exposed basin floor that some reconstructions propose. This was a deep, hypersaline sea, still filled with kilometers of water, but water so salty that it could no longer support most forms of marine life. The surface may have looked calm, perhaps slightly oily in texture due to the high salinity. The color may have been different, less blue, more green or gray, depending on the concentration of dissolved minerals and the types of microorganisms that could survive in such extreme conditions. The 35,000 years of this first phase represent a period of adjustment. The basin was responding to the loss of Atlantic inflow, but it had not yet reached the most extreme conditions. Water was still present. The sea level had dropped, perhaps by tens or even hundreds of meters, but the basin was not empty. The transformation was underway, but it was still in its early stages. What would follow in the next phase would be far more severe. The eastern Mediterranean basin is deeper than the western basin. The Ionian and Herodotus subbasins, located in the eastern section, descend to depths exceeding 4 kilometers below the surface. These deep depressions are separated from the shallower western Mediterranean by the Sicily Sill, a submerged ridge that rises to within a few hundred meters of the surface under normal conditions. This internal topography would prove critical during the crisis, creating different environments in different parts of the basin as water levels fell and salinity rose. During the first phase of salt accumulation, which lasted approximately 35,000 years, halite deposition occurred exclusively in the eastern Mediterranean. This geographic restriction tells us something important about the hydrological state of the basin during this period. If the entire Mediterranean had been uniformly desiccated, if water levels had dropped equally across the basin, we would expect to see salt deposits forming everywhere at roughly the same time. But that is not what the geological record shows. The eastern basin was precipitating salt, while the western basin was not. This means the two regions were experiencing different conditions. The most likely explanation is that the Sicily Sill acted as a threshold. dividing the Mediterranean into two semi-independent hydrological systems once the Atlantic connection was sufficiently restricted. Water could still flow across the sill, but the exchange was limited. The eastern basin, being deeper and more isolated, began to concentrate its dissolved salts more rapidly than the western basin. As evaporation removed water from the surface, the remaining water became denser and saltier. This dense brine sank to the bottom of the deep eastern subbasins, accumulating in the lowest depressions. The salinity required for halite precipitation is extreme. Normal seawater contains approximately 35 grams of dissolved salts per litre of water, or 35 parts per thousand. For halite to begin crystallizing, seawater must be concentrated to about 350 parts per thousand, roughly 10 times normal salinity. This level of concentration occurs only when a significant percentage of the water has evaporated. In the case of the eastern Mediterranean during the first phase, this means that the water column, though still present and deep, had lost enough volume through evaporation that the remaining brine was saturated with sodium chloride. The process of halite formation is straightforward. As water evaporates, the concentration of dissolved ions increases. Sodium and chloride ions, which are the most abundant dissolved salts in seawater, eventually reach a concentration where they can no longer remain in solution. Crystals begin to form, first as tiny nuclei, then growing as more ions attach to the crystal lattice. These crystals are denser than the surrounding brine, so they sink, settling onto the seafloor in a slow, continuous rain of salt. Over 35,000 years, this rain of halite crystals built up layers of salt on the floor of the eastern basin. The accumulation was not rapid in human terms, a few millimeters per year perhaps, but over millennia, millimeters become meters. By the end of the first phase, substantial deposits of halite had accumulated in the deepest parts of the eastern basin, layers that would eventually contribute to the kilometre-thick salt giant that defines the Messinian sedimentary record. What did this eastern brine look like? It would not have resembled normal seawater. The colour would have been different, likely more opaque, perhaps with a greenish or milky tint due to the high concentration of dissolved minerals. The density would have been noticeably higher. If you could stand at the edge and observe the surface, you might notice that waves behave differently, moving more slowly, dissipating more quickly due to the increased viscosity of the brine. The temperature of the brine would have varied with depth and season, but the high salinity would have affected the thermal properties of the water. Hypersaline brines tend to stratify strongly, with dense, cold brine sitting at the bottom and warmer, slightly less saline water near the surface. This stratification would have limited vertical mixing, creating a stable, layered water column where the deep brine remained isolated from the surface for long periods. Life in this environment would have been sparse. Most marine organisms cannot tolerate salinities above about 60 parts per thousand. At concentrations 10 times that level, essentially nothing multicellular survives. Perhaps some extremophile bacteria, organisms adapted to hypersaline conditions, could have persisted in certain zones. But the rich, diverse marine ecosystems that had inhabited the Mediterranean under normal conditions would have been absent. The deep eastern basins during this phase were likely biological deserts, quiet and still, with only the slow accumulation of salt crystals marking the passage of time. The western basin, meanwhile, remained less affected. It was closer to the Atlantic connection, shallower on average, and separated from the eastern basin by the Sicily sill. It likely retained more normal salinity for a longer period, though it too was experiencing increased salt concentrations as evaporation continued. But it had not yet reached the point of halite precipitation. That would come later, in the second phase, when the crisis intensified and the entire basin underwent a rapid, dramatic transformation. The 35,000 years of the first phase represent a period of regional differentiation, where the Mediterranean's internal geography created different hydrological regimes in different areas. The eastern basin was accumulating salt. The western basin was not. This asymmetry would persist and even intensify as the crisis progressed. Understanding this spatial variation is essential to understanding the full complexity of what occurred during the Messinian salinity crisis. It was not a uniform event. It was a mosaic of conditions shaped by the interplay of evaporation, basin geometry, and the degree of isolation from the Atlantic. The second phase of the Messinian salinity crisis was fundamentally different from the first, where the initial phase had lasted 35,000 years and involved gradual salt accumulation in the eastern basin. The second phase was rapid and catastrophic. It occurred in less than 10,000 years. The sea level drop during this phase was not gradual. It was a plunge. The evidence for this rapid drawdown comes from multiple geological indicators. The chlorine isotope composition of halite deposits shows a sharp shift between the first and second phases, indicating a sudden change in the hydrological balance of the basin. Sediment cores taken from various locations across the Mediterranean reveal layers of evaporites that accumulated quickly, suggesting a dramatic acceleration in the rate of evaporation and salt deposition. The distribution of these deposits, which appear across the entire basin rather than just in the eastern section, indicates that the second phase affected the Mediterranean as a whole. What triggered this rapid transition? The most likely explanation is that the Atlantic connection, which had been restricted but not entirely severed during the first phase, was now completely blocked. Whatever minimal inflow had been sustaining the basin, keeping it largely brine-filled despite ongoing evaporation, was cut off. The Mediterranean was now a closed basin, hydrologically isolated from the global ocean. Evaporation continued at its relentless pace. But there was no replacement water. The basin began to drain. The rate of sea level fall during this phase would have been visibly rapid on human timescales. If the net evaporative loss was approximately 0.5 meter per year, then in a single human lifetime, the sea level would drop by tens of meters. In 1,000 years, hundreds of meters. The shoreline would retreat. Coastal areas that had been submerged would emerge as dry land. The continental shelves, normally underwater, would be exposed. The spatial pattern of the drawdown was not uniform. The eastern basin experienced a more severe drop than the western basin. Sea level in the eastern Mediterranean fell between 1.7 and 2.1 kilometers. In the western Mediterranean, the drop was approximately 850 meters. This asymmetry was again due to the Sicily Sill. As the Mediterranean's overall water level fell, the sill eventually emerged above the surface of the remaining water in the western basin, creating a physical barrier between the two regions. From that point forward, the eastern and western basins evolved independently, each losing water according to its own evaporative regime. The eastern basin, being deeper, had farther to fall. Even after losing 1.7 to 2.1 kilometers of sea level, the deepest subbasins likely remained filled with brine. The Ionian and Herodotus subbasins, with their original depths exceeding 4 kilometers, would have retained over a kilometer of water even at the lowest point of the crisis. But the margins of the eastern basin, the continental shelves and slopes, would have been completely desiccated. The sea, which had once lapped against the coasts of what are now Greece, Turkey, Egypt, and the Levant, had retreated into the deep central basins, leaving vast expanses of exposed seafloor. The western basin experienced a less severe drawdown. At 850 meters, the sea level drop was still dramatic, but the shallower average depth of the western Mediterranean meant that less of the basin remained submerged. Large areas of seafloor would have been exposed, but deep brine pools likely persisted in the deepest parts of the Alboran and Algerian basins. The Sicily Sill now emerged as a land bridge, separated the two brine-filled depressions, creating two independent hypersaline lakes where a continuous sea had once existed. As the water level dropped, halite precipitation accelerated. With less water remaining in the basin, the concentration of dissolved salts increased rapidly. The brine became saturated, then supersaturated. Halite crystals formed in enormous quantities, settling onto the seafloor in thick layers. This was the period of maximum salt accumulation, when the vast majority of the Mediterranean salt giant was deposited. In less than 10,000 years, a volume of salt exceeding 1 million cubic kilometers was precipitated from the brine and accumulated on the basin floor. The sheer scale of this salt accumulation is difficult to comprehend. 1 million cubic kilometers of halite corresponds to a mass of approximately 2.2 times 10 to the 18th kilograms. If spread evenly across the Mediterranean sea floor, it would form a layer roughly a kilometer thick. In reality, the salt deposits are not uniform. They are thickest in the deep basins, where the brine was most concentrated and where salt accumulated over the longest period. In some locations, the evaporite layers exceed 2 kilometers in thickness. The landscape during this phase would have been alien. If the basin was largely desiccated, as the classical model suggests, then the exposed seafloor would have been a vast salt plain stretching for hundreds of kilometers. The surface would have been white or light grey, covered in halite crystals that formed as brine, evaporated in shallow pools and playas scattered across the basin floor. The air would have been hot and dry. There would have been no vegetation, no animals, no sound except the wind moving across the empty expanse. If the basin retained deep brine pools, as the alternative model proposes, then the landscape would have been different but no less extreme. The exposed margins would still have been salt flats, but instead of emptiness at the basin centre, there would have been vast lakes of hypersaline brine, kilometres deep, their surfaces lying far below global sea level. The brine would have been so dense that it might have appeared almost syrupy, its surface calm and still, reflecting the sky with an unnatural clarity. Either way, this was no longer a sea in any recognisable sense. It was a geological process made visible, a hydrological system in collapse transforming before the indifferent passage of geological time. The Mediterranean had become a crucible of evaporation, a place where water was being removed and salt was being left behind at a rate and scale that few other places on Earth have ever experienced. The question of what the Mediterranean actually looked like during the maximum drawdown of the Messinian salinity crisis remains one of the most debated topics in Mediterranean geology. Two competing models have been proposed, each supported by different interpretations of the geological evidence. The debate is not merely academic. It affects how we reconstruct the past environment, how we understand the mechanisms of salt deposition, and how we assess the economic potential of hydrocarbon resources buried beneath the Mediterranean seafloor. The classical model, which has dominated scientific thinking for over 4 decades, is known as the deep basin shallow water scenario. This model proposes that the Mediterranean desiccated almost completely during the peak of the crisis. Sea level dropped by more than 1,500 meters, possibly exceeding 2,000 meters in the eastern basin. The deep basins were largely exposed to the atmosphere. What remained was not a sea, but a series of shallow, ephemeral salt lakes scattered across the basin floor, surrounded by vast expanses of dry, exposed seafloor lying thousands of meters below global sea level. The primary evidence supporting this model comes from the discovery of shallow water fossil fauna within sediments now located on the abyssal plain. These organisms, based on their morphology and ecological requirements, lived in shallow water, no more than a few tens of meters deep. Yet the sediments containing these fossils are now buried beneath kilometers of water. The only way to explain their presence, according to the classical model, is if the abyssal plain was once exposed or covered only by shallow water, allowing these organisms to colonize the area before being buried by later sediments. Additional support for the deep basin shallow water model comes from erosional features on the continental margins. The most famous of these is the buried Nile Canyon, a deep gorge carved into the continental shelf and slope off the coast of Egypt. The canyon extends far below the present seafloor and far inland, where it has been identified beneath the modern Nile Delta. For a river to carve such a deep canyon, its base level, the level to which the river erodes, must have been substantially lower than the present sea level. Early interpretations of the Nile Canyon suggested that the Mediterranean sea level must have dropped by more than 2,000 meters to explain the depth and extent of the erosion. If the classical model is correct, then the Messinian Mediterranean was one of the most extreme landscapes in Earth's recent geological history. Imagine standing on the rim of what is now the continental shelf, looking down into a chasm more than a kilometer deep. The basin floor would stretch to the horizon, a salt desert interrupted occasionally by shallow, hypersaline lakes. The air would shimmer with heat. There would be no sound of waves, no smell of the sea, only the vast silence of an empty basin. But the classical model has faced significant challenges in recent years. The alternative model, sometimes called the deep water non-desiccated scenario, proposes that the Mediterranean never dried out completely. Instead, it retained large volumes of water throughout the crisis, though that water was highly restricted and hypersaline. According to this model, sea level dropped substantially, but not catastrophically. The basin remained filled with brine, and salt deposition occurred within this deep, persistent brine pool rather than on an exposed desert floor. The most compelling evidence for this alternative model comes from a 2022 re-evaluation of the Nile Canyon. Using modern techniques, researchers removed the effects of post-Messinian sediment loading, accounted for flexural isostasy, the bending of the Earth's crust in response to changing loads, and corrected for sediment compaction. These adjustments revealed that the original depth of the canyon's base level was likely only about 600 meters below present sea level, 2 to 4 times smaller than previous estimates. This suggests that the Mediterranean drawdown, while severe, was not as extreme as the classical model proposes. A drawdown of 600 meters is still substantial. It is roughly 5 times greater than the sea level drops that occurred during Pleistocene glaciations. It would have exposed the continental shelves and upper slopes, creating dramatic changes in the basin's geography. But it would not have emptied the deep basins. The Ionian, Herodotus, Alboran, and Algerian subbasins would have remained filled with brine, possibly 1 to 3 kilometers deep. Salt deposition could have occurred through precipitation from this deep brine, settling onto the seafloor in layers that accumulated over tens of thousands of years. The choice between these two models fundamentally changes how we visualize the Messinian landscape. In the classical model, the Mediterranean is a desert, a vast empty basin with only scattered shallow lakes. In the alternative model, it is a hypersaline sea, smaller and shallower than before, but still a body of water of considerable size and depth. The basin is not empty, it is transformed. The debate also has implications for understanding how specific geological features formed. The Mediterranean seafloor is marked by large submarine channel systems, particularly in the Levant Basin off the coast of Israel and Lebanon. If the basin was largely dry during the crisis, these channels must have been carved by rivers flowing across the exposed seafloor, descending from the continental margins toward the lowest points of the basin. If the basin retained deep water, the channels could have formed through submarine processes, carved by density currents, underwater flows of sediment-laden water that moved across the seafloor under the influence of gravity. The resolution of this debate is important for practical reasons as well. Petroleum geologists use models of the Messinian salinity crisis to assess the potential for hydrocarbon accumulation in the deep Mediterranean. The classical model suggests that organic-rich sediments, the source rocks for petroleum, would have been deposited primarily in shallow anoxic lakes scattered across the basin floor. The alternative model suggests that source rocks would have been more widely distributed, deposited in deep anoxic brine pools that covered larger areas of the basin. The two models lead to different predictions about where oil and gas might be found, and in what quantities. For now, the question remains open. Both models are supported by different lines of evidence. Both are consistent with certain aspects of the geological record. The true answer may lie somewhere between the two extremes, with the basin experiencing variable conditions over the 400,000 years of the crisis, sometimes more desiccated, sometimes retaining more water, depending on the precise degree of isolation and the climatic conditions at any given time. What is certain is that the Mediterranean during the Messinian salinity crisis was unlike any marine environment that exists today, whether it was a desert or a brine pool or some combination of both at different times and places. It was a landscape of extremes, shaped by forces operating at the intersection of tectonics, climate, and hydrology. Beneath the floor of the modern Mediterranean Sea lies a geological formation known as the Mediterranean Salt Giant. It is one of the largest evaporite deposits on Earth, a layer of halite, gypsum, and anhydrite that stretches across the entire basin, buried beneath hundreds of meters of younger sediments. The formation is so large and so distinct that it can be mapped using seismic reflection techniques, where sound waves are sent down through the seafloor and the returning echoes reveal the structure of the underlying rock layers. On seismic profiles, the top of the salt giant appears as a bright, continuous reflector, marking the boundary between the Messinian evaporites below and the Pliocene marine sediments above. The volume of this salt deposit is staggering. Conservative estimates place it at greater than 1 million cubic kilometers. To put this in perspective, if you could somehow gather all of this salt and spread it evenly across the entire surface area of the Mediterranean, it would form a layer approximately 1 kilometer thick. The mass of the salt is approximately 2.2 times 10 to the 18th kilograms. This is not a localized deposit. It is a pan-Mediterranean phenomenon, evidence of a basin-wide hydrological crisis that affected every part of the sea. The formation of such a massive salt deposit requires the evaporation of an enormous volume of seawater. Halite constitutes only about 3.5% of the dissolved solids in normal seawater. To produce 1 cubic kilometer of halite, you need to evaporate roughly 30 cubic kilometers of seawater. To produce 1 million cubic kilometers of halite, you need to evaporate approximately 30 million cubic kilometers of seawater. The modern Mediterranean contains only about 3.7 million cubic kilometers of water. This means that to form the salt giant, the basin would have had to be filled and evaporated multiple times, or sustained by a continuous but slow supply of water that was then evaporated, leaving the salt behind. The question of where all this water came from and where it went is central to understanding the Messinian salinity crisis. If the basin was completely isolated from the Atlantic, then the only sources of water would have been rivers flowing into the Mediterranean and atmospheric precipitation falling directly onto the basin. Even if we assume that runoff rates were higher during the Messinian than they are today, it is difficult to account for the volume of water needed to produce the observed salt deposits through runoff alone. One possibility is that the Atlantic connection was never completely closed, but was instead severely restricted. A small, continuous trickle of Atlantic water could have entered the basin, just enough to supply the dissolved salts needed for evaporite formation, but not enough to offset the evaporative loss and maintain sea level. This water would have been immediately concentrated by evaporation, precipitating its dissolved salts and contributing to the growing layers of halite and gypsum on the basin floor. Another possibility is that the connection opened and closed cyclically, controlled by the interplay of tectonic uplift and climate-driven sea level changes. During periods when global sea level was high, Atlantic water could have flowed into the Mediterranean, refilling the basin and restoring more normal marine conditions. During periods when sea level was low, the connection would have been severed, and evaporation would have dominated once again. This cyclical model is supported by the observation that the evaporite deposits are layered, suggesting repeated episodes of salt precipitation separated by intervals of different conditions. The actual composition of the salt giant provides clues about the conditions under which it formed. The deposits are not uniform. They consist of multiple layers or cycles, each representing a distinct phase of evaporation. The most common minerals are gypsum, calcium sulfate dihydrate, and anhydrite, calcium sulfate without water. These minerals precipitate from seawater before halite does, when the brine is concentrated to about 3 to 5 times normal salinity. Halite only begins to precipitate when the brine is concentrated to about 10 times normal salinity. The sequence of mineral precipitation follows a predictable pattern. As seawater evaporates, the first minerals to crystallize are carbonates, such as calcite, which precipitate when the brine is concentrated to about 2 times normal salinity. As evaporation continues, gypsum begins to form. Further evaporation leads to halite precipitation. If the evaporation is extreme, reaching concentrations 20 to 30 times normal salinity, more exotic salts such as sylvite, potassium chloride and carnallite, a potassium-magnesium chloride, begin to precipitate. These highly soluble salts are relatively rare in the Mediterranean deposits, suggesting that the brine rarely reached such extreme concentrations. The thickness of the evaporite layers varies across the basin. In the deep central basins where the brine was deepest and evaporation could proceed over longer periods, the salt layers are thickest, sometimes exceeding 2 kilometers. On the continental margins and in shallower areas, the deposits are thinner, reflecting the fact that these areas were exposed earlier in the drawdown and experienced less salt accumulation. The distribution of the evaporites mirrors the topography of the pre-crisis seafloor, with thick deposits in the lows and thin deposits, or no deposits at all, on the highs. The salt giant is not just a curiosity for geologists. It has significant economic importance. Evaporite deposits are valuable natural resources. Halite is mined for table salt, road salt, and chemical feedstock. Gypsum is used in construction materials, particularly wallboard and plaster. Potash salts, though less common in the Mediterranean deposits, are essential for fertilizer production. Salt deposits also play a role in petroleum geology. The thick, impermeable layers of halite and anhydrite can act as seals, trapping oil and gas in underlying rock formations and preventing their migration to the surface. The presence of the salt giant also affects the structural geology of the Mediterranean. Salt is a relatively weak material under geological conditions. It can flow and deform more easily than most other types of rock. When buried beneath thick layers of younger sediments, salt can begin to move, squeezing upward in response to the weight of the overlying material. This process, known as salt tectonics, can create complex geological structures such as salt domes, diapirs, and walls. These structures are common in the Mediterranean and are often associated with oil and gas accumulation. Understanding the salt giant requires understanding the conditions that formed it. It is not simply a layer of salt. It is a record of 400,000 years of hydrological crisis, a geological archive that preserves information about the Mediterranean's isolation, the degree of evaporation, the chemistry of the brine, and the cyclical nature of the crisis. Each layer of gypsum, each bed of halite, each thin interval of different minerals, tells a story about the conditions that existed at a specific moment in the Messinian. The salt giant is a monument to evaporation, to the slow, patient removal of water from a restricted basin, grain by grain, crystal by crystal, over a timescale that dwarfs human history. The Messinian salinity crisis was not only a hydrological and geological event, it was also an ecological catastrophe. The Mediterranean Sea before the crisis supported a diverse and complex marine ecosystem. Thousands of species inhabited the basin, from microscopic plankton drifting in the surface waters to bottom-dwelling organisms living in the deep-sea sediments. Fish, mollusks, crustaceans, marine mammals, and countless other forms of life had evolved over millions of years, adapted to the specific conditions of the Mediterranean environment. The crisis destroyed most of this biological diversity. As the Atlantic connection closed and salinity began to rise, marine organisms faced an immediate and escalating threat. Most marine life is adapted to a narrow range of salinity, typically between 30 and 40 parts per thousand. Deviations from this range, even by a few parts per thousand, can cause stress. Large deviations are lethal. As the Mediterranean salinity increased due to evaporation and the loss of Atlantic inflow, the water became progressively more hostile to life. Different organisms have different tolerances for salinity changes. Some species, known as euryhaline organisms, can tolerate a wide range of salinities. These include certain types of fish, crustaceans, and mollusks that are adapted to estuarine environments where freshwater and seawater mix. Other species, known as stenohaline organisms, can only survive within a narrow salinity range. Most open ocean marine species fall into this category. They are precisely adapted to the stable salinity of the ocean and have little ability to cope with rapid changes. As Mediterranean salinity rose above 40 parts per thousand, stenohaline species would have been the first to die. Coral reefs, which require stable salinity and temperature conditions, would have bleached and died. Many species of fish that depended on coral habitats would have disappeared. Planktonic organisms, the foundation of the marine food web, would have declined as salinity exceeded their tolerance limits. The die-off would have cascaded through the ecosystem, affecting predators that depended on these species for food. As salinity continued to rise, reaching 60, 80, or 100 parts per thousand, even euryhaline species would have struggled. At these concentrations, the osmotic stress on marine organisms becomes severe. Water is pulled out of cells by the high salt concentration in the surrounding environment. Proteins denature, metabolic processes fail. Eventually, even the most tolerant species reach their physiological limits and die. By the time the Mediterranean reached the halite precipitation stage, with salinities exceeding 300 parts per thousand, essentially all multicellular marine life would have been extinct. The water would have been toxic to everything except certain extremophile bacteria and archaea, microorganisms adapted to hypersaline environments such as salt flats and evaporation ponds. These extremophiles can survive and even thrive in conditions that would kill any other form of life, but they do not constitute an ecosystem in any meaningful sense. They are survivors in a dead sea. The fossil record confirms this ecological collapse. Sediments deposited during the peak of the Messinian salinity crisis contain very few fossils. The diversity of species drops precipitously. Marine microfossils such as Foraminifera and Coccolithophores, which are usually abundant in marine sediments, become rare or absent. The sediments are often barren, sterile layers of evaporites with little or no biological content. This absence of life is stark compared to the rich fossil assemblages found in sediments deposited before and after the crisis. Research indicates that approximately 89% of endemic Mediterranean species went extinct during the Messinian salinity crisis. Endemic species are those found nowhere else, species that had evolved specifically within the Mediterranean and were adapted to its unique conditions. When the crisis struck, these species had no refuge. They could not migrate to other ocean basins because they were isolated by the geography of the Mediterranean. They could not adapt quickly enough to the rapidly changing conditions. They simply died. The 89% extinction rate is comparable to some of the major mass extinction events in Earth's history. It is higher than the extinction rate observed at the end of the Cretaceous, when the dinosaurs disappeared. It is a testament to the severity of the environmental change that occurred during the Messinian. The Mediterranean, which had been a thriving marine ecosystem, was transformed into a biological wasteland in a span of time that was geologically rapid but still extended over tens of thousands of years. The few species that survived were likely those with the broadest salinity tolerance, or those that could find refuge in marginal environments where conditions were less extreme. Coastal lagoons, river mouths, and isolated pockets of less saline water may have served as refugia, allowing some populations to persist through the worst of the crisis. But these survivors were a tiny fraction of the original diversity. The collapse of the marine ecosystem would have had cascading effects beyond the basin itself. Seabirds that fed on Mediterranean fish would have lost their food source. Coastal ecosystems that depended on marine nutrients would have been disrupted. The absence of marine productivity would have altered nutrient cycles across the region. The Mediterranean, which had been a productive marine environment contributing to the broader biological and chemical cycles of the planet, became ecologically inert. The extinction was not instantaneous. It unfolded over thousands of years, tracking the rise in salinity and the progressive loss of habitat. Species that could tolerate moderate salinity increases survived longer. Species with more limited tolerances disappeared earlier. The result was a stepwise collapse, with biodiversity declining in stages as conditions worsened. By the time the crisis reached its peak, the Mediterranean was effectively lifeless, a chemical system rather than a biological one, a place where geological processes dominated and life had been reduced to a trace presence. The drop in Mediterranean sea level during the Messinian salinity crisis did not only affect the basin itself, it profoundly altered the behavior of rivers that flowed into the Mediterranean from the surrounding continents. These rivers, which had previously entered the sea at or near sea level, now found themselves flowing toward a base level that had dropped by hundreds or even thousands of meters. The response was immediate and dramatic. The rivers accelerated. They carved deep gorges into the continental margins. They transformed the landscape for hundreds of kilometers inland. A river's base level is the lowest point to which it can erode. For rivers that flow into the ocean, sea level is the base level. When sea level drops, the base level drops with it. The river responds by cutting downward, eroding its channel in an attempt to reach the new, lower base level. The steeper the gradient between the river's source and its base level, the more energetic the erosion. During the Messinian, when Mediterranean sea level dropped by hundreds of meters in the western basin and nearly 2 kilometers in the eastern basin, the gradient became extraordinarily steep. The Nile River provides the most extensively studied example of this erosional response. The Nile, which flows northward from East Africa and empties into the Mediterranean along the coast of Egypt, carved a deep canyon into the continental shelf and slope during the Messinian. This buried canyon has been mapped using seismic reflection techniques and by drilling through the sediments that now fill it. The canyon extends far below the present seafloor and can be traced inland beneath the modern Nile Delta. The depth and extent of the Nile Canyon indicate that the river was responding to a dramatically lowered base level. The canyon reaches depths of several hundred meters below the present sea level. It extends upstream for hundreds of kilometers, far beyond the current coastline. Tributaries that fed into the main Nile also carved deep channels, creating a dendritic network of erosion that spread across the landscape. The volume of material removed by this erosion is immense, representing millions of cubic meters of rock and sediment transported downstream and deposited in the Mediterranean basin. The Nile was not alone. Other major rivers that flow into the Mediterranean underwent similar transformations. The Rhône River, which flows from the Alps through southeastern France and enters the Mediterranean near Marseille, carved a deep canyon into the continental margin. This canyon has been identified in seismic surveys and contains sediments that can be dated to the Messinian. The canyon's depth and structure indicate that the Rhône, like the Nile, was responding to a base level that had dropped by hundreds of meters. The Ebro River in northeastern Spain also carved a deep canyon during the Messinian. The buried canyon has been mapped beneath the modern Ebro Delta and can be traced upstream into the interior of the Iberian Peninsula. Smaller rivers around the Mediterranean periphery, from the Po in northern Italy to rivers in North Africa and the eastern Mediterranean, all show evidence of deep erosion during this period. The Messinian salinity crisis triggered a wave of erosion that affected not just the Mediterranean basin, but the entire surrounding continental margin. The process of canyon formation during the Messinian would have been visually dramatic if anyone had been there to witness it. As the sea level dropped, the river would have cascaded over the edge of the newly exposed continental shelf, creating waterfalls that migrated upstream as the river continued to erode downward. The waterfalls would have been sites of intense erosion, where the falling water carved plunge pools and undercut the rock, causing blocks to collapse and the waterfall to retreat further upstream. Over thousands of years, these waterfalls migrated inland, leaving behind deep, steep-walled canyons. The canyons would have resembled the Grand Canyon in the southwestern United States, though formed by different processes. The Grand Canyon was carved over millions of years by the Colorado River cutting through horizontally layered rock. The Messinian canyons were carved much more rapidly, in tens of thousands of years, driven by the sudden and extreme lowering of base level caused by the Mediterranean's drawdown. The sediment eroded from these canyons did not disappear. It was transported downstream by the rivers and deposited in the Mediterranean basin. During the period of maximum drawdown, when the basin floor was exposed or covered only by shallow brine, the rivers would have flowed across vast salt flats before reaching whatever water remained. The sediment would have been deposited as alluvial fans and deltas spreading out across the basin floor. These deposits are now buried beneath younger sediments, but they can be identified in sediment cores and seismic profiles as distinct layers of clastic material, sand, silt, and clay, interbedded with the evaporites that characterize the Messinian. The erosional impact of the Messinian extended beyond the river valleys themselves. The lowering of base level affected groundwater systems across the surrounding continents. Groundwater naturally flows toward the lowest point in the landscape, which for coastal regions is sea level. When Mediterranean sea level dropped, groundwater tables also dropped, following the new lower base level. This would have caused springs and wells to dry up. It would have altered the hydrology of entire regions, affecting vegetation patterns and the availability of water for terrestrial ecosystems. The canyons carved during the Messinian are now largely hidden beneath younger sediments. After the Mediterranean refilled at the end of the crisis, the rivers lost their steep gradients and began to deposit sediment rather than erode. The canyons filled with marine and fluvial sediments over the following millions of years. Today, they can only be detected through geophysical surveys and drilling, but their presence is a testament to the profound impact that the Messinian salinity crisis had on the surrounding landscape, reshaping not just the basin itself, but the continental margins for hundreds of kilometers around it. When the Mediterranean sea level dropped during the Messinian salinity crisis, large areas of seafloor that had been submerged for millions of years were exposed to the atmosphere. The continental shelves, normally underwater, became dry land. The Sicily Sill, which had separated the western and eastern Mediterranean basins, emerged as a land bridge connecting what are now Sicily and Tunisia. And most significantly, the Strait of Gibraltar, the narrow passage that had been the Mediterranean's last connection to the Atlantic, was exposed as a land corridor connecting the Iberian Peninsula to North Africa. the emergence of the Gibraltar land bridge had profound consequences for the distribution of terrestrial fauna. Before the Mycenaean, Africa and Europe had been separated by a marine barrier. Animals could not cross from one continent to the other unless they could swim or fly. The presence of the strait maintained this separation, even though the distance across the water was relatively small. But once the strait emerged as dry land, that barrier disappeared. A terrestrial pathway opened between two continents that had been isolated from each other for millions of years. The paleontological record provides clear evidence of faunal exchange across the Gibraltar corridor during the Mycenaean. Fossil assemblages from this period in southern Spain and northern Morocco show the appearance of species that had previously been restricted to one continent or the other. African mammals migrated into Europe. European mammals migrated into Africa. The mixing of these faunal communities created a unique biogeographic signature that can be traced in the fossil record. Among the species that crossed from Africa to Europe during the Mycenaean were certain types of rodents. Mice and other small mammals that had evolved in Africa found their way into the Iberian Peninsula. These animals were adapted to arid environments, capable of surviving in the hot, dry conditions that would have characterized the exposed Mediterranean basin and its surroundings. Their presence in European fossil sites from this period is evidence that a land connection existed, because small mammals like mice are not capable of crossing wide stretches of open ocean. Larger mammals also made the crossing. Camels, which had originated in North America but had migrated to Asia and Africa, appear in European fossil sites during the Mycenaean. Their presence indicates that the land bridge was not just a narrow, inhospitable corridor, but a viable migration route capable of supporting the movement of large herbivores. Camels would have needed access to vegetation and water along the route, suggesting that the exposed corridor was not entirely barren. The migration was not one-directional. European species also moved into Africa. The fossil record from North Africa shows the appearance of certain European mammal species during the Mycenaean that were not present before. The exchange created a temporary mixing of faunal communities, a brief interval when animals from two long-separated continents shared the same landscape. What would the Gibraltar land bridge have looked like? The exposed seafloor of the strait would have been relatively flat, composed of marine sediments that had accumulated on the bottom over millions of years. These sediments, once submerged, were now drying in the sun. Cracks would have formed as the sediments desiccated. Salt deposits would have been present in low-lying areas where seawater had been trapped and evaporated. The landscape would have been barren, at least initially, with little vegetation because the soils were marine in origin and not immediately suitable for plant growth. Over time, however, some colonization by plants would have occurred. Wind-dispersed seeds could have arrived from the surrounding continental margins. Drought-resistant plants adapted to saline soils might have established themselves in certain areas. River valleys descending from the highlands of Gibraltar and Morocco might have carried fresh water and sediment, creating more favorable conditions for vegetation. But overall, the land bridge would have been a harsh environment, dry, salty, and exposed. The animals that crossed the land bridge would have done so in response to various pressures. Some may have been following expanding or contracting vegetation zones driven by climate change. Others may have been fleeing competition or predation on their home continent. Still others may have simply been dispersing, spreading into new territories as populations grew. The exact motivations are impossible to determine from the fossil record alone, but the fact that migrations occurred is clear. The Sicily Sill, which emerged as a land bridge between Sicily and North Africa, likely also facilitated some faunal exchange, though the record is less clear. The Sill's emergence would have connected the islands of the central Mediterranean to the African mainland, potentially allowing terrestrial animals to colonize islands that are now separated by deep water. The biogeographic patterns of certain Mediterranean island species show evidence of dispersal events that may date to the Mycenaean, though disentangling the timing of these events from other dispersal routes, such as rafting on vegetation mats, is challenging. The existence of these land bridges was temporary. They lasted only as long as the Mediterranean remained in its drawn-down state. Once the basin refilled at the end of the crisis, the seafloor was submerged again. The land bridges disappeared. The faunal communities that had mixed during the Mycenaean were separated once more, but the genetic and evolutionary legacy of this brief interval of connection persisted. The descendants of animals that crossed during the Mycenaean continued to inhabit their new continents, contributing to the biogeographic patterns that we observe in the fossil record and in living species today. The water that evaporated from the Mediterranean during the Mycenaean salinity crisis did not disappear. It entered the atmosphere as water vapor, transported by winds and weather systems, and eventually fell as precipitation somewhere else on Earth. The hydrological cycle ensured that the water removed from the Mediterranean was redistributed across the planet. Most of it returned to the ocean, falling as rain over the Atlantic, Pacific, Indian, and other ocean basins. A smaller fraction fell as snow on ice sheets or as rain on continents, where it entered rivers and eventually flowed back to the sea. The redistribution of this water had a measurable effect on global sea level. The volume of water stored in the Mediterranean under normal conditions is approximately 3.7 million cubic kilometers. During the Mycenaean, much of this volume was removed and dispersed globally. Even if the Mediterranean never dried out completely, retaining deep brine pools in the central basins, a significant volume of water, perhaps 1 to 2 million cubic kilometers, was transferred from the Mediterranean to the global ocean system. When this water was added to the world ocean, which has a surface area of roughly 361 million square kilometers, global sea level rose. The amount of the rise can be calculated by dividing the volume of water transferred by the surface area of the ocean. If 1 million cubic kilometers of water was transferred, global sea level would have risen by approximately 2.8 meters. If 2 million cubic kilometers were transferred, the rise would have been about 5.5 meters. Most estimates place the global sea level rise caused by the Mycenaean salinity crisis at around 10 meters. 10 meters may not sound like a large change compared to the depth of the ocean, which averages about 3,700 meters. But for coastal regions, a 10-meter rise in sea level is substantial. Coastlines around the world would have shifted inland. Low-lying areas would have been flooded. River deltas would have been submerged. Islands with low elevation would have been reduced in size or disappeared entirely. The impact would have been global, affecting every continent and every ocean basin. The rise in sea level would have occurred gradually, over the same timescale as the Mediterranean's drawdown. If the drawdown took tens of thousands of years, the sea level rise would also have unfolded over tens of thousands of years. This is slow compared to human timescales, but relatively rapid in geological terms. Coastal ecosystems would have had to migrate inland or adapt to changing conditions. Coral reefs growing on shallow platforms would have had to grow upward to keep pace with rising sea level, or risk being drowned in water too deep for their light requirements. The global sea level rise caused by the Mycenaean would have left traces in the geological record. Sedimentary sequences from this period in coastal regions around the world should show evidence of marine transgression, the landward migration of the shoreline. Shallow marine sediments should overlie terrestrial or coastal sediments, recording the flooding of previously dry land. In practice, identifying these traces is challenging because the signal is small and can be obscured by local tectonic movements, sediment supply variations, and other factors. But in regions with good stratigraphic control, the signature of the Mycenaean sea level rise can be detected. The transfer of water from the Mediterranean to the global ocean also had a secondary, more subtle effect. When water evaporates from a restricted basin like the Mediterranean, it leaves behind dissolved salts. These salts accumulate in the basin as evaporite deposits. The water that evaporates and returns to the global ocean is fresh, or nearly fresh, because the evaporation process does not transfer dissolved salts into water vapor. This means that the salinity of the world ocean decreased slightly as a result of the Mycenaean. The decrease in global ocean salinity was small, perhaps a fraction of 1 part per thousand, but it was not negligible. Even small changes in salinity can have important effects on ocean circulation and climate because salinity affects water density. Denser water sinks, driving deep ocean currents that transport heat and nutrients around the planet. A reduction in salinity makes water less dense, which can alter circulation patterns. One of the consequences of reduced salinity is a higher freezing point. Freshwater freezes at 0 degrees Celsius, while seawater with a salinity of about 35 parts per thousand freezes at approximately negative 1.9 degrees Celsius. If the salinity of seawater decreases, the freezing point rises, making it easier for sea ice to form. During the Mycenaean, when the world ocean salinity was reduced by the sequestration of salt in the Mediterranean, the freezing point of seawater would have been slightly higher. This would have facilitated the formation of sea ice in polar regions, particularly in the Arctic and around Antarctica. The growth of sea ice has a feedback effect on climate. Ice reflects sunlight more effectively than open water, a property known as albedo. When sea ice expands, more sunlight is reflected back into space, reducing the amount of solar energy absorbed by the Earth. This cooling effect can promote further ice growth, creating a positive feedback loop. Some researchers have suggested that the salinity reduction caused by the Mycenaean salinity crisis may have contributed to the onset or intensification of glaciation in the Northern Hemisphere, which was beginning to develop during the late Miocene. The connection between Mediterranean salt sequestration and global climate is not straightforward. Many factors influence the growth of ice sheets, including atmospheric carbon dioxide levels, orbital variations, and continental configurations. But the Mycenaean salinity crisis occurred during a period when Earth's climate was transitioning toward cooler conditions and when ice sheets were starting to grow in the Northern Hemisphere. The timing suggests that the Mediterranean event may have played a role, however small, in this broader climatic shift. The global effects of the Mycenaean salinity crisis illustrate an important principle in Earth science. Regional events can have planetary consequences. A hydrological crisis confined to one relatively small ocean basin, the Mediterranean represents less than 1% of the world ocean's volume, produced measurable changes in sea level and ocean chemistry worldwide. The sequestration of salt altered the salinity of the global ocean. The redistribution of water raised sea level along coastlines thousands of kilometers from the Mediterranean. The potential impact on ice sheet growth may have influenced climate for millions of years to come. The Mediterranean, isolated and evaporating, was not a closed system. It was connected to the planet through the atmosphere, through ocean circulation, and through the complex web of feedbacks that link water, climate, and life. The late Miocene was a period of transition in Earth's climate. Global temperatures, which had been relatively warm during the early and middle Miocene, were beginning to decline. Ice sheets, which had existed primarily in Antarctica for tens of millions of years, were starting to form in the Northern Hemisphere. This cooling trend would eventually lead to the Pleistocene ice ages, when massive ice sheets covered much of North America, Europe, and Asia. But during the late Miocene, the transition was just beginning. The climate was cooler than it had been, but not yet as cold as it would become. The growth of ice sheets is controlled by several factors. Temperature is the most obvious. If summers are not warm enough to melt the previous winter's snow, ice accumulates year after year, gradually building into a glacier. But temperature alone is not sufficient. Ice sheets also require moisture. Snow must fall in large quantities for ice to accumulate. Regions that are extremely cold but also extremely dry, such as parts of Antarctica's interior, accumulate ice slowly because snowfall is limited. Ocean circulation plays a critical role in delivering moisture to high-latitude regions where ice sheets form. Warm ocean currents transport heat and water vapor from the tropics toward the poles. When this moist air encounters cold conditions over land or sea ice, it condenses and falls as snow. The efficiency of this moisture delivery depends on the temperature and salinity structure of the ocean, because these properties control the density of seawater and, consequently, the strength and pattern of ocean currents. The Mycenaean salinity crisis altered the salinity structure of the world ocean in a subtle but potentially significant way. By sequestering an enormous quantity of salt in the Mediterranean basin, the crisis reduced the overall salinity of the global ocean. This reduction was small in absolute terms, perhaps a few tenths of a part per thousand, but it was distributed across the entire ocean. Every cubic meter of seawater became slightly less salty. A reduction in salinity has a direct effect on the freezing point of seawater. The freezing point of fresh water is 0 degrees Celsius. The freezing point of seawater with a salinity of 35 parts per thousand is approximately negative 1.9 degrees Celsius. The relationship is linear. For every decrease in salinity, the freezing point rises. If the salinity of the world ocean decreased by even a small amount, the freezing point would have increased, making it easier for sea ice to form at high latitudes. Sea ice formation has important consequences for climate. When seawater freezes, it excludes most of the dissolved salts, leaving behind a layer of relatively fresh ice floating on the surface. The salt that is excluded is concentrated in the water immediately below the ice, creating dense, cold brine that sinks. This sinking brine drives deep ocean circulation, a process known as thermohaline circulation. The strength of this circulation depends on the density contrast between surface and a deep water, which is controlled by temperature and salinity. Changes in thermohaline circulation can affect the distribution of heat around the planet. Warm water from the tropics is transported toward the poles by surface currents. At high latitudes, this water cools, becomes denser, and sinks, forming deep currents that flow back toward the equator. This circulation pattern transfers heat from the equator to the poles, moderating global temperature contrasts. If the circulation weakens or shifts, the distribution of heat changes, potentially leading to regional cooling or warming. The reduction in ocean salinity caused by the Messinian could have influenced thermohaline circulation by altering the density structure of the ocean. Lower salinity water is less dense, which could weaken the sinking of cold water at high latitudes. However, the formation of sea ice, facilitated by the higher freezing point, would have produced dense brine that could compensate for the reduced salinity. The net effect is difficult to predict without detailed modelling, but the potential for impact is clear. Another way in which the Messinian could have influenced climate is through its effect on sea ice extent. If the reduced salinity and higher freezing point allowed sea ice to expand over a larger area, the increased albedo, the reflectivity of ice compared to open water, would have caused more sunlight to be reflected back into space. This would have reduced the amount of solar energy absorbed by the Earth, leading to cooling. Cooling, in turn, could have promoted further sea ice growth and possibly the expansion of glaciers on land, creating a positive feedback loop. The timing of the Messinian salinity crisis, between 597 and 5.33 million years ago, coincides roughly with evidence for increased ice volume in the northern hemisphere. Oxygen isotope records from deep-sea sediments show a shift toward heavier isotope values during this period, indicating that more water was being stored in ice sheets on land. The correlation is not perfect, and it is difficult to establish a direct causal link between the Mediterranean event and northern hemisphere glaciation. But the coincidence in timing has led some researchers to propose that the Messinian may have acted as a trigger or amplifier for ice sheet growth. The mechanism would work as follows. The sequestration of salt in the Mediterranean reduced global ocean salinity. The reduced salinity raised the freezing point of seawater, facilitating sea ice formation at high latitudes. The expanded sea ice increased Earth's albedo, reducing solar energy absorption and causing cooling. The cooling promoted snowfall and glacier growth on land, particularly in regions like Greenland, northern Canada, and Scandinavia, where ice sheets would later dominate during the Pleistocene. The ice sheets, once initiated, could persist and grow due to their own feedback effects, even after the Mediterranean refilled and ocean salinity returned to normal. This hypothesis remains speculative, proving it would require detailed climate modelling that accounts for the complex interactions between ocean salinity, circulation, sea ice, atmospheric temperature, and ice sheet dynamics. But it illustrates an important point. The Earth system is interconnected. A hydrological crisis in one relatively small basin can potentially influence ice sheets thousands of kilometers away, altering the trajectory of global climate for millions of years. The relationship between salt and ice, between the evaporating Mediterranean and the growing glaciers of the northern hemisphere, is one of the more intriguing aspects of the Messinian salinity crisis. It suggests that the crisis was not merely a regional event, but a planetary one, with consequences that extended far beyond the basin itself. The salt deposited on the Mediterranean seafloor, the water redistributed to the global ocean, the reduction in salinity, the potential for increased sea ice and glaciation, all of these are threads in a larger story about how Earth's climate system responds to perturbations, how feedbacks amplify small changes, and how events separated by vast distances can be linked through the global circulation of water, heat, and salt. The final phase of the Messinian salinity crisis, known as the Lago Mare event, was fundamentally different from the phases that preceded it. Where the earlier stages had been defined by hypersalinity, extreme salt concentrations, and the precipitation of massive evaporite deposits, the Lago Mare phase was characterized by a dramatic shift toward lower salinity. The water in the Mediterranean, which had been a concentrated brine hostile to most forms of life, became brackish or even fresh. This reversal occurred approximately 5.50 million years ago and lasted until the end of the crisis at 533 million years ago. The name Lago Mare comes from Italian and means lake sea. It reflects the idea that the Mediterranean during this final phase was not fully marine in character, but had characteristics more similar to a large lake or a series of lakes with variable salinity. The water chemistry was dominated not by marine salts, but by a mix of freshwater and evaporitic salts, creating conditions that could support organisms adapted to brackish environments, but that were inhospitable to normal marine species. The evidence for this shift in salinity comes from several sources. The sediments deposited during the Lago Mare phase are distinct from the earlier Messinian evaporites. They include layers of gypsum, but the gypsum is often interbedded with clays, silts, and other clastic sediments that indicate the presence of freshwater input. The evaporites themselves show characteristics consistent with precipitation from water, with lower salinity, between 5 and 60 parts per thousand, compared to the 130 to 320 parts per thousand typical of the high salinity brines that formed the earlier halite deposits. Another line of evidence comes from the fossil record. The Lago Mare sediments contain distinctive fossil assemblages that are different from both the earlier Messinian deposits and the marine sediments that would be deposited after the crisis ended. The fossils include microfauna, tiny organisms such as ostracods and foraminifera that are characteristic of brackish or freshwater environments. These organisms belong to what is known as the Paratethyan biophases, species that were typical of the Paratethys, a large ancient sea that covered parts of what are now Eastern Europe and Central Asia. The presence of Paratethyan species in the Mediterranean during the Lago Mare phase suggests a connection between the two basins, or at least a source of fresh water from the Paratethyan region. The traditional interpretation has been that the Paratethys, which was a massive body of water, possibly overflowed into the Mediterranean basin, flooding it with brackish water and introducing Paratethyan organisms into the Mediterranean. This overflow model has been widely accepted for decades and fits with the idea of the Mediterranean as a single flooded lake sea during the final phase of the crisis. However, recent research has challenged this basin-wide overflow model. Time probabilistic analyses of sedimentary cycles at 24 sites around the Mediterranean have revealed patterns that are inconsistent with a single, unified lake sea. Instead, the data suggests that the Lago Mare sediments were deposited in disconnected shallow lacustrine environments. These were not parts of a single large lake, but rather separate, independent basins, each with its own hydrology, each responding to local climate conditions rather than to a massive influx of water from the Paratethys. The sedimentary cycles preserved in Lago Mare deposits are related to precession, the wobble in Earth's axis of rotation that occurs over a cycle of approximately 21,000 years. Precession affects the seasonal distribution of solar radiation, which in turn influences precipitation patterns and the amount of fresh water flowing into basins. If the Lago Mare phase consisted of disconnected lakes, each one would have experienced cyclical changes in water level and salinity driven by these precession-controlled climate variations. The lakes would have filled during wetter periods and evaporated during drier periods, creating the interbedded evaporite and clastic sediments observed in the geological record. The shift from hypersaline to brackish conditions during the Lago Mare phase requires a significant change in the water budget of the Mediterranean. Instead of evaporation vastly exceeding freshwater input, as had been the case during the earlier phases, freshwater input must have increased substantially. There are two possible sources for this increased freshwater: rivers and precipitation. Climate models for the late Miocene suggest that the region experienced periods of increased rainfall during this time, driven by changes in atmospheric circulation patterns linked to orbital variations. Increased precipitation over the Mediterranean basin and its surrounding drainage basins would have led to higher river discharge, delivering more fresh water to the basin. If the Paratethys did contribute water to the Mediterranean during the Lago Mare phase, it would have been through river systems draining from the Paratethys region rather than through a direct overflow. The Danube River, which today drains much of Central and Eastern Europe and empties into the Black Sea, may have had a different course during the Mycenaean, potentially delivering Paratethian water to the Mediterranean. Other rivers draining the Balkans and Anatolia could also have contributed. The salinity during the Lago Mare phase, estimated at between 5 and 60 parts per thousand, represents a wide range. A salinity of 5 parts per thousand is essentially fresh, comparable to water in estuaries or coastal lagoons. A salinity of 60 parts per thousand is still brackish, significantly saltier than normal seawater, but far less concentrated than the brines of the earlier phases. This variability suggests that conditions were not uniform across the basin or over time. Some areas and some periods may have been nearly fresh, while others remained moderately saline. The interbedded nature of the Lago Mare sediments, alternating layers of evaporites and clastics, indicates that the basins experienced repeated cycles of filling and drying. During wetter climatic phases, freshwater input would have exceeded evaporation, causing the lakes to expand and salinity to decrease. Clastic sediments, sands, silts and clays would have been deposited by rivers and in the shallow lake margins. During drier phases, evaporation would have exceeded input, causing the lakes to shrink and salinity to increase. Evaporites would have precipitated in the drying margins of the lakes. These cycles would have occurred on time scales of thousands to tens of thousands of years, following the precessional rhythm of Earth's orbital variations. Each cycle would have left a distinct layer in the sedimentary record, creating a stratigraphy that can be read like a history book, recording the alternation between wetter and drier conditions throughout the Lago Mare phase. The Lago Mare reversal represents a temporary reprieve from the extreme conditions of the earlier Mycenaean phases. The Mediterranean, which had been a hypersaline death trap, became a brackish environment capable of supporting some forms of life. But this reversal was not a return to normal marine conditions. The basin was still isolated from the Atlantic, or connected only tenuously. The water chemistry was still abnormal, and the ecosystem, though more diverse than during the hypersaline phases, was still impoverished compared to what had existed before the crisis. The Lago Mare phase was not a recovery. It was an interlude, a brief interval of different conditions before the final catastrophic event that would end the crisis entirely. The organisms that appeared in the Mediterranean during the Lago Mare phase were not the marine species that had inhabited the basin before the crisis began. They were different, adapted to conditions that no marine organism could tolerate, yet unable to survive in fully fresh water either. These were creatures of the brackish zone, the transitional realm between ocean and river, between salt and fresh. And they came from the Paratethys. The Paratethys was an ancient sea that covered vast areas of what is now Eastern Europe, Central Asia, and parts of the Middle East. During the Miocene, it stretched from the region of the modern Black Sea eastward through the Caspian Basin and beyond. It was not fully connected to the world ocean. Like the Mediterranean during the Mycenaean, the Paratethys was a restricted basin, subject to its own cycles of evaporation and refilling, its own unique environmental conditions. Over millions of years, the organisms living in the Paratethys had evolved to tolerate variable and often reduced salinity, adapting to an environment that was neither fully marine nor fully fresh. When conditions in the Mediterranean shifted during the Lago Mare phase, creating brackish environments across parts of the basin, these Paratethian species found a habitat they could occupy. Between approximately 5.40 and 5.33 million years ago, a diverse assemblage of Paratethian organisms appeared in Mediterranean sediments. These included ostracods, small crustaceans with bivalved shells, foraminifera, single-celled organisms with chambered shells, mollusks adapted to low salinity water, and possibly fish species that could tolerate brackish conditions. The appearance of these organisms in the Mediterranean raises questions about how they arrived. The traditional explanation, as mentioned in the previous chapter, was that the Paratethys overflowed directly into the Mediterranean, creating a massive influx of water that carried organisms with it. But if the recent interpretation is correct, that the Lago Mare phase consisted of disconnected lakes rather than a single flooded basin, then the mechanism of dispersal must have been different. One possibility is that organisms migrated through river systems. If rivers draining from the Paratethyan region flowed into the Mediterranean during this period, they could have served as corridors for dispersal. Brackish water species living in the lower reaches of these rivers could have been transported downstream during floods, or could have actively migrated along the river corridors into the Mediterranean basins. Once there, they would have found suitable habitat in the brackish lakes and lagoons that characterized the Lago Mare environment. Another possibility is that the organisms were transported by birds. Aquatic birds can carry small organisms, or their eggs and resting stages, on their feet, feathers, or in their digestive tracts. A bird feeding in a Paratethyan lake could inadvertently carry ostracod eggs or foraminifera to a distant Mediterranean lake, introducing the species to a new habitat. This mechanism, known as passive dispersal, is effective over surprisingly large distances and can explain how aquatic organisms colonize isolated water bodies that have no direct hydrological connection. A third possibility is that there was, at times, a direct hydrological connection between the Paratethys and Mediterranean, but that this connection was intermittent and localized rather than a massive basin-wide overflow. During particularly wet climatic phases, when precipitation was high and river discharge was strong, temporary spillways could have opened between the two basins, allowing water and organisms to flow from one to the other. These connections would have been ephemeral, lasting only as long as water levels remained high enough to overtop the topographic barriers separating the basins. Regardless of the mechanism, the result was the same. Paratethyan species colonized the Mediterranean during the Lago Mare phase, establishing populations that persisted for tens of thousands of years. The fossil record shows that these organisms were widely distributed across the Mediterranean region, found in sediments from Spain to Turkey, from Italy to North Africa. This wide distribution indicates that the brackish conditions that characterized the Lago Mare phase were not confined to a single location but were widespread, creating suitable habitat across much of the basin. The salinity range that these organisms could tolerate, between 5 and 60 parts per thousand, corresponds closely to the estimated salinity of the Lago Mare water masses. This is not a coincidence. The organisms were adapted to these specific conditions. They could not have survived the hypersaline brines of the earlier Messinian phases, when salinity exceeded 300 parts per thousand, and they would have struggled in fully marine conditions with salinity around 35 parts per thousand, because they had evolved in the Paratethys under different conditions. The Lago Mare phase provided a unique window of opportunity, a brief interval when the Mediterranean's environmental conditions matched the tolerances of Paratethyan species. The diversity of the Lago Mare fauna was limited compared to a typical marine ecosystem. There were no coral reefs, no large predatory fish, no complex food webs involving multiple trophic levels, but within the constraints of the brackish environment, there was still biological activity. Ostracods grazed on algae and organic particles in the sediment. Foraminifera filtered food from the water column. Mollusks burrowed in the mud of shallow lake margins. These organisms were not building a thriving ecosystem, but they were present, and their presence indicates that the Mediterranean during the Lago Mare phase was not entirely lifeless. The duration of the Paratethyan occupation was relatively short in geological terms. The Lago Mare phase lasted from approximately 5.50 to 5.33 million years ago, a span of roughly 170,000 years. But the peak of Paratethyan diversity occurred in the latter part of this interval, between 540 and 533 million years ago, a period of about 70,000 years. After that, the crisis ended abruptly with the refilling of the Mediterranean, and fully marine conditions returned. The Paratethyan species, adapted to brackish water, could not survive the sudden return of normal oceanic salinity. They disappeared from the Mediterranean as quickly as they had arrived. The Lago Mare fauna represents an ecological snapshot of a transitional moment. It shows that even during the most extreme phases of the Messinian salinity crisis, life found a way to persist, not the diverse marine life that had existed before, but specialized organisms adapted to harsh and variable conditions. The Paratethyan invasion was temporary, opportunistic, and ultimately doomed to end when the Mediterranean reconnected to the Atlantic. But for a brief interval in deep time, the Mediterranean was home to a community of organisms from a distant sea, refugees in a brackish refuge. The Messenian salinity crisis, from its beginning at 597 million years ago to its end at 533 million years ago, lasted approximately 400,000 years. This is not a number easily grasped by human intuition. 400,000 years is longer than our species, Homo sapiens, has existed. It is longer than the entire span of recorded human history repeated 200 times. It encompasses thousands of human generations, were there humans to count them, which there were not. The Miocene Earth was populated by other creatures, early hominids in Africa, mastodons and saber-toothed cats, forests and grasslands shaped by animals and climates that would become extinct or transform long before the first humans walked. Yet, in geological terms, 400,000 years is brief. It is less than 1/10 of 1% of Earth's age. It is a fraction of the time required for major evolutionary transitions, for mountain ranges to rise significantly, for continents to drift measurable distances. The Messenian salinity crisis was both immense and fleeting, depending on the timescale against which it is measured. During those 400,000 years, the Mediterranean passed through multiple states. It began as a stable marine environment, connected to the Atlantic, supporting diverse ecosystems. It transitioned to a restricted basin with rising salinity as the Atlantic connection weakened. It entered a phase of deep-water brine accumulation in the eastern basin, where salt precipitated from hypersaline waters, while the western basin remained less affected. It underwent a rapid drawdown, losing kilometers of sea level in less than 10,000 years, exposing vast areas of seafloor or concentrating water into deep brine pools. It experienced the Lago Mare reversal, when brackish conditions temporarily replaced hypersalinity and paratethnian organisms colonized the basin. Each of these phases left its signature in the geological record. Sediment cores extracted from beneath the Mediterranean seafloor contain layers that can be analyzed, dated, and interpreted. Seismic surveys reveal the structure of the buried evaporite deposits, their thickness, their distribution, their internal layering. Fossil assemblages document the changes in biological communities as conditions shifted. Chemical analyses of the evaporites themselves, particularly the isotopic composition of chlorine, oxygen, and other elements, provide information about water sources, evaporation rates, and the degree of hydrological restriction. From these diverse lines of evidence, scientists have reconstructed the sequence of events. The reconstruction is not complete. There are gaps in the record, intervals where sediments have been eroded or were never deposited. There are ambiguities in interpretation, different scientists drawing different conclusions from the same data. But the overall narrative is clear. The Mediterranean was isolated. It evaporated. Salt accumulated. Conditions fluctuated. And then, at 533 million years ago, the crisis ended. The end, when it came, was not gradual. It was not a slow restoration of Atlantic inflow allowing the basin to refill over tens of thousands of years. It was catastrophic. The barrier at the Strait of Gibraltar, which had held back the Atlantic Ocean for hundreds of millennia, failed. Water rushed through the breach. The Mediterranean, which had been a collection of hypersaline lakes, brackish basins, and possibly exposed salt flats, was inundated by a flood of staggering magnitude. Before examining the flood itself, it is worth pausing to consider the state of the Mediterranean immediately before the breach. At 533 million years ago, the basin was in its Lago Mare phase. Sediments from this period show brackish conditions, with salinity somewhere between 5 and 60 parts per thousand. The basin likely consisted of multiple disconnected lakes occupying the deeper parts of the Mediterranean depression. These lakes were separated by exposed ridges and sills that had emerged as sea level dropped during the earlier phases of the crisis. The surrounding landscape would have been shaped by 400,000 years of altered hydrology. Rivers had carved deep canyons into the continental margins, responding to the lowered base level. These canyons descended steeply from the continental shelves, cutting through sedimentary layers and bedrock, creating dramatic relief. The Gibraltar corridor was probably a dry land bridge, or perhaps occupied by a shallow, intermittent river, draining whatever Atlantic water occasionally spilled over the sill during high sea level stands. The climate in the Mediterranean region during the late Mycenaean was likely arid or semi-arid. The presence of the exposed basin floor would have created its own microclimate. Large expanses of salt flats and dry lake beds would have reflected solar radiation, creating high surface temperatures during the day and rapid cooling at night. Dust storms would have been common, carrying fine sediment from the exposed basin floor and depositing it across the surrounding continents. Vegetation on the continental margins may have been sparse, limited to areas with access to groundwater or river corridors. The Gibraltar sill itself, the topographic barrier separating the Atlantic from the Mediterranean, was probably not a simple, uniform ridge. It would have had a complex structure with higher and lower sections, channels carved by past water flows, and perhaps weak zones where erosion had thinned the rock. The height of the sill relative to the Atlantic sea level outside and the Mediterranean water level inside would have determined the hydraulic head, the pressure difference driving water flow once a breach occurred. If the Mediterranean water level was substantially below Atlantic sea level, as the geological evidence suggests, the hydraulic head could have been hundreds or even over 1,000 meters. This means that once the barrier began to fail, the pressure difference would have driven water through the breach with tremendous force. The flow would have accelerated rapidly, eroding the rock around the breach and widening the opening. A small initial breach could grow into a massive channel in a short time, a process known as catastrophic erosion. The question of what triggered the final breach remains open. It may have been tectonic activity, an earthquake that fractured the rock forming the sill. It may have been erosion, slow or sudden, that finally cut through the barrier. It may have been a climatic event, a period of high Atlantic sea level that increased the hydraulic head to the point where the barrier could no longer hold. Or it may have been some combination of these factors, operating together to overcome the threshold that had kept the Atlantic and Mediterranean separated for 400,000 years. Whatever the trigger, once the breach occurred, the consequences were inevitable. The Atlantic Ocean, with its immense volume and the pressure of a 1,000-meter hydraulic head, would not be denied. The water would flow, the Mediterranean would fill, and the landscape shaped by 400,000 years of isolation and evaporation would be transformed in a matter of months or years. The patience of the crisis, its slow accumulation of change over vast stretches of time, was about to be answered by the violence of the deluge. At 533 million years ago, the Atlantic Ocean broke through the barrier at the Strait of Gibraltar and began to refill the Mediterranean basin. This event is known as the Zanclean Flood, named after the Zanclean age of the Pliocene epoch, which it marks the beginning of. The flood was one of the largest and most rapid hydrological events in recent geological history, comparable in some ways to the catastrophic floods that carved the channeled scablands of eastern Washington during the Pleistocene, but far larger in total volume. The scale of the flood can be quantified through several parameters. The maximum discharge rate, the volume of water flowing through the strait per unit time, has been estimated at between 68 and 100 sverdrups. A sverdrup is a unit of flow equal to 1 million cubic meters per second. For comparison, the Amazon River, the largest river on Earth by discharge, flows at approximately 0.2 sverdrups. The Zanclean flood, at its peak, carried water at a rate roughly 500 to 1,000 times greater than the Amazon. The vertical drop at the breach point was estimated to exceed 1,000 meters. This means that Atlantic water flowing through the strait would have cascaded over a cliff more than a kilometer high, descending into the Mediterranean basin in a waterfall of planetary scale. No waterfall of this magnitude exists on Earth today. The largest contemporary waterfalls, such as Angel Falls in Venezuela, have drops of around 800 meters and carry far less water. The Zanclean cataract would have dwarfed them in both height and volume. The duration of the main flooding phase, the period during which the bulk of the Mediterranean was refilled, has been estimated at between several months and 2 years. This estimate is based on calculations that account for the cross-sectional area of the strait, the hydraulic head driving the flow, and the volume of water needed to fill the basin. 90% of the Mediterranean's volume was restored during this brief interval. The sea level within the basin rose at rates that may have exceeded 10 meters per day during the peak of the flood. 10 meters per day is an almost incomprehensible rate of sea level rise. It means that coastlines retreated by hundreds of meters or kilometers each day, depending on the slope of the seafloor. Areas that had been dry land for hundreds of thousands of years were submerged within weeks. The canyons that rivers had carved into the continental margins were inundated, becoming submarine valleys once again. The salt flats that may have covered the exposed basin floor were buried beneath rapidly accumulating marine sediments. The erosional power of the flood was immense. As water accelerated through the strait and descended the vertical drop into the basin, it carried tremendous kinetic energy. This energy was expended on the seafloor and the rocks forming the passage, scouring channels, transporting sediment, and reshaping the submarine topography. The evidence for this erosion has been preserved in the geological record and can be observed using modern geophysical techniques. Seismic reflection surveys of the Sicily Sill, the submerged ridge separating the western and eastern Mediterranean, have revealed over 300 asymmetric, streamlined ridges carved into the seafloor. These ridges have a morphology consistent with erosion by large-scale turbulent water flow. They are oriented in a northeasterly direction, pointing from the western Mediterranean toward the eastern basin, indicating the direction of flow as the flood surge passed across the sill. The ridges are not random. They are organized in a pattern that reflects the dynamics of the floodwater as it moved across the sill. In some areas, the ridges are closely spaced, indicating zones of particularly intense erosion. In other areas, they are more widely spaced or absent, suggesting regions where the flow was less concentrated or where the substrate was more resistant to erosion. The streamlined shape of the ridges, with blunt upstream ends and tapered downstream ends, is diagnostic of high-velocity water flow, similar to features formed by glacial meltwater floods or by tidal currents in shallow seas. Seismic data has also revealed a large W-shaped channel carved into the continental shelf east of the Sicily Sill. This channel connects the area of streamlined ridges to the deep Noto Canyon, a submarine valley that descends into the eastern Mediterranean basin. The W shape, with multiple parallel troughs, suggests that the floodwater was organized into several braided streams as it crossed the sill and then converged into the canyon. The channel acted as a funnel, directing the massive discharge of water from the western basin into the deep eastern basin. Computer modeling of the flood, using the topography of the seafloor and the estimated discharge rates, suggests that flow velocities reached up to 32 meters per second in certain locations. This is hurricane force velocity, sufficient to erode rock, transport boulders, and create the large-scale bedforms observed in the seismic data. The turbulence of the flow would have been extreme, with water churning and mixing as it descended the waterfall and spread across the basin floor. The sound of the flood would have been deafening, had there been anyone to hear it. A waterfall carrying 100 million cubic meters of water per second over a vertical drop of more than a kilometer would have generated a roar audible for hundreds of kilometers. The impact of the falling water on the basin floor would have created vibrations that might have been felt as far away as the coastlines of North Africa and southern Europe. The mist and spray thrown up by the cataract would have created a permanent cloud above the strait, visible from great distances. The path of the floodwater can be traced through the Mediterranean. It entered through the Strait of Gibraltar, filling the western basin first. As the water level in the western basin rose, it eventually overtopped the Sicily Sill, which had been exposed during the crisis. Water then cascaded across the sill into the eastern basin, repeating the waterfall phenomenon on a slightly smaller scale. The eastern basin, being deeper, took longer to fill, but the process was still rapid by geological standards. The refilling was not uniform. The deepest parts of the basin filled first, creating a rising sea that gradually submerged the margins. Islands that had existed as high points on the exposed basin floor became true islands once again, then disappeared as the water rose above their peaks. The land bridges that had connected continents and allowed mammal migrations were severed. The Gibraltar Corridor, which had been a terrestrial pathway, became a marine strait. The Sicily Sill, which had been a land bridge, became a submerged ridge. The sediments deposited during the flood are distinct from both the underlying Messinian evaporites and the overlying normal marine sediments of the Pliocene. They consist of coarse clastics, sands and gravels, transported by the high-velocity flow and deposited in fans and deltas where the flow decelerated. These sediments contain clasts, rock fragments, derived from the erosion of the strait and the surrounding seafloor, providing physical evidence of the flood's erosional power. The Zanclean flood was not a gradual process. It was a catastrophe in the technical sense of the term, a sudden, dramatic change in state driven by the crossing of a threshold. For 400,000 years, the Mediterranean had been isolated, evaporating, accumulating salt, and supporting only limited and specialized forms of life. In less than 2 years, it was transformed back into a marine basin filled with Atlantic water, reconnected to the global ocean, and ready to be recolonized by marine organisms. The patience of the crisis gave way to the violence of the restoration. The Zanclean flood did not proceed at a constant rate. Like most catastrophic hydrological events, it likely went through several phases as conditions changed and the system evolved. Understanding these phases requires considering the physical processes that controlled the flow, the height of the barrier, the cross-sectional area of the breach, the hydraulic head, and the feedback between erosion and flow velocity. In the initial phase, when the barrier first failed, the breach would have been relatively small. Perhaps it was a crack in the rock, a weakness exploited by erosion or opened by tectonic movement. Water would have begun to flow through this small opening, accelerating due to the hydraulic head created by the difference in elevation between the Atlantic sea level and the Mediterranean water level. The initial flow might have been modest by the standards of what would come later, but it would have carried significant erosive power. As water flowed through the breach, it would have begun to erode the surrounding rock. The erosion would have been concentrated at the base of the flow, where velocity was highest and where the turbulent water could pluck away particles and dissolve minerals. The breach would have widened and deepened. As it grew, the cross-sectional area available for flow increased, allowing more water to pass through. The increased flow would have accelerated the erosion, creating a positive feedback loop. More flow meant more erosion. More erosion meant a larger opening. A larger opening meant even more flow. This process, known as headward erosion or nick point retreat, is common in river systems where a sudden drop in base level causes rapid downcutting. But the scale of the Zanclean flood was far beyond anything observed in typical river systems. The hydraulic head was over 1,000 meters. The volume of water available was effectively infinite, supplied by the Atlantic Ocean. And the rock forming the barrier, while substantial, was ultimately incapable of resisting the erosive force of water moving at such high velocities and carrying such immense kinetic energy. As the breach expanded, the discharge rate increased. Early in the flood, the flow might have been in the range of a few sverdrups, comparable to the largest river floods on Earth. But as the breach widened, the discharge would have climbed rapidly. 10 sverdrups, 20, 50, eventually reaching the estimated maximum of 68 to 100 sverdrups. At this stage, the flood would have been fully developed, a torrent of water pouring through a channel that may have been kilometers wide, descending a vertical drop of more than a kilometer, and spreading across the Mediterranean basin with a front that advanced visibly hour by hour. The Mediterranean basin did not fill uniformly. The deepest parts filled first. Water flowing through the strait would have descended to the lowest elevations, pooling in the deep Alboran and Algerian basins of the western Mediterranean. As these basins filled, the water level rose until it reached the next topographic threshold, the Sicily Sill. Once the water overtopped this sill, it would have cascaded into the eastern Mediterranean, filling the Ionian and Herodotus basins in the same way the western basins had been filled. The Sicily Sill was lower than the Gibraltar Sill, so the waterfall across the Sicily Sill would have been less dramatic. But it was still substantial. Estimates suggest a drop of several hundred meters, perhaps 500 to 800 meters, depending on the precise elevation of the sill relative to the water level in the western basin at the time of overtopping. The flow velocities across the Sicily Sill, as recorded by the erosional features described in the previous chapter, reached up to 32 meters per second, sufficient to carve the streamlined ridges and the W-shaped channel that still mark the seafloor today. As the eastern basin filled, the remaining areas of exposed seafloor and shallow brine pools were progressively submerged. The brackish lakes of the Lago Mare phase disappeared beneath the rising seawater. The salt flats, if they existed, were buried. The canyons carved by rivers into the continental margins became submarine features, their steep walls now thousands of meters below the surface. The continental shelves, which had been dry land for hundreds of thousands of years, were flooded, creating shallow marine environments suitable for the colonization by coastal organisms. The rate of sea level rise within the basin during the peak of the flood was extraordinary. If 90% of the Mediterranean's volume was restored in 2 years, that corresponds to an average rate of approximately 1.7 million cubic kilometers per year, or about 4,600 cubic kilometers per day. Given that the surface area of the Mediterranean is about 2.5 million square kilometers, this translates to an average sea level rise of roughly 1.8 meters per day. But the rise would not have been constant. It would have been faster during the peak discharge and slower during the early and late phases of the flood. At the peak, when discharge reached 100 sverdrups, the rate of sea level rise could have exceeded 10 meters per day in localized areas, particularly in the deeper basins where water was accumulating most rapidly. The environmental consequences of such rapid flooding would have been severe for any terrestrial organisms living on the exposed basin floor or the continental margins. Animals would have had little time to migrate to higher ground. Plants would have been submerged before they could disperse seeds or establish in new locations. The ecosystems that had colonized the exposed areas during the crisis, whatever they were, would have been destroyed. But these were probably marginal ecosystems to begin with, limited by the harsh conditions of aridity, salinity, and isolation. Their loss, while locally catastrophic, was part of the larger transformation as the Mediterranean returned to a marine state. The flood also had consequences for the water chemistry of the basin. The incoming Atlantic water had normal oceanic salinity, approximately 35 parts per thousand. As it mixed with whatever water remained in the Mediterranean, whether hypersaline brine in the deep basins or brackish Lago Mare water in shallow lakes, the salinity would have rapidly adjusted toward oceanic values. The mixing would not have been instantaneous. Density differences between fresh and saline water can create stratification, with denser water sinking and lighter water remaining at the surface. But the turbulence of the flood, the high velocities, and the sheer volume of water pouring into the basin would have promoted mixing, ensuring that the entire water column approached normal marine salinity within a relatively short time. The temperature of the incoming Atlantic water would also have affected conditions in the basin. Atlantic surface water in this region is typically cooler than Mediterranean surface water due to the influence of deeper, colder Atlantic currents. The influx of cooler water would have lowered the average temperature of the Mediterranean, at least initially, until thermal equilibrium was re-established through solar heating and atmospheric exchange. By the end of the flood, the Mediterranean had been transformed. The basin that had been a collection of hypersaline and brackish lakes, or possibly a vast salt desert, was once again a marine basin, filled with seawater, connected to the Atlantic Ocean, and poised to be recolonized by marine organisms from the Atlantic and beyond. The flood had erased 400,000 years of isolation in less than 2 years. The rapidity of this reversal, the contrast between the slow accumulation of the crisis and the sudden violence of its termination, is one of the most striking aspects of the Messinian salinity crisis. It illustrates a fundamental characteristic of Earth's systems. They can persist in one state for long periods, accumulating stress and potential energy, and then flip to a new state in a geological instant when a threshold is crossed. The Zanclean flood ended the Messinian salinity crisis, but it did not immediately restore the Mediterranean to its pre-crisis state. The refilling of the basin with Atlantic water was a necessary condition for recovery, but it was not sufficient. The ecosystems that had thrived before the crisis were gone. 89% of endemic Mediterranean species had gone extinct. The seafloor was covered with a thick layer of evaporites and flood-deposited sediments. The water chemistry, though returned to normal marine salinity, still carried traces of the brine that had occupied the basin during the crisis. Recovery would not be a matter of months or years. It would take millions of years. The first organisms to recolonize the Mediterranean were likely those with the greatest dispersal ability and the broadest environmental tolerances. Planktonic species, carried by ocean currents from the Atlantic, would have been among the first to arrive. These include foraminifera, coccolithophores, diatoms, and other microscopic organisms that drift in the surface waters. Their rapid reproduction rates and ability to form dormant stages that can survive adverse conditions made them well suited to colonize the newly marine basin. Benthic organisms, those that live on or in the seafloor, would have followed. Larvae of mollusks, echinoderms, crustaceans, and other bottom-dwelling invertebrates can be transported long distances by ocean currents before settling and metamorphosing into adult forms. These organisms would have found a seafloor quite different from what their ancestors had inhabited before the crisis. Instead of the normal marine sediments, mud and sand with a diverse community of burrowing organisms, they encountered evaporites, hardened salt layers, and freshly deposited flood sediments. Fish and other mobile species could have entered the Mediterranean through the Strait of Gibraltar as soon as the connection to the Atlantic was re-established. But colonization is not the same as establishing a stable, self-sustaining population. Species need to find suitable habitat, adequate food resources, and conditions appropriate for reproduction. In the immediate aftermath of the flood, the Mediterranean was a biological desert, a vast volume of water with very little productivity and few ecological niches occupied. Productivity in marine ecosystems depends on nutrients. In the ocean, primary production, the conversion of sunlight and nutrients into organic matter by photosynthetic organisms, occurs primarily in the surface waters where light is available. But the nutrients required for this process, particularly nitrogen and phosphorus, are often depleted in surface waters and must be replenished through upwelling, the vertical transport of nutrient-rich deep water to the surface. Upwelling is driven by wind patterns, ocean currents, and the interaction of water masses with seafloor topography. In the newly refilled Mediterranean, the patterns of circulation and upwelling would have been different from those that existed before the crisis. The water column was more homogeneous, lacking the vertical structure that develops over time as different water masses interact and stratify. The deep water had not yet accumulated the nutrients that would sink from the surface as organisms died and decomposed. The system needed time to develop the complexity that characterizes a mature marine environment. As productivity gradually increased, supported by nutrients imported from the Atlantic and delivered by rivers, the base of the food web began to rebuild. Phytoplankton populations grew. Zooplankton that fed on the phytoplankton increased in abundance. Small fish that fed on zooplankton colonized the basin. Larger fish that preyed on smaller fish followed. Each trophic level had to be established before the next could thrive, and this progression took time. The seafloor community also developed slowly. Deposit feeders, organisms that ingest sediment and extract organic matter from it, were among the first benthic colonizers. They could survive on whatever sparse organic material settled from the surface waters. Filter feeders, organisms that extract particles from the water column, required higher levels of productivity before they could establish viable populations. Predators and scavengers came later, once there were sufficient prey populations to support them. Coral reefs, which had existed in the Mediterranean before the crisis, did not return immediately. Reef-building corals require stable, clear water with specific temperature and salinity ranges. They are sensitive to sediment, which can clog their feeding structures and block light needed by their symbiotic algae. The Mediterranean in the early Pliocene, immediately after the flood, was not an ideal environment for coral growth. Sediment input from rivers and from the reworking of flood deposits would have kept turbidity high. Water chemistry may have been slightly different from pre-crisis conditions, and perhaps most importantly, the source populations of reef-building corals in the Atlantic or the Indo-Pacific would have needed time to disperse into the Mediterranean and find suitable substrate for colonization. The process of biodiversity recovery, the gradual return of species richness to pre-crisis levels, took approximately 1.7 million years. This figure comes from analyses of fossil assemblages in sediments deposited after the Zanclean flood. By tracking the number of species present at different time intervals, paleontologists can estimate how long it took for diversity to reach levels comparable to those that existed before the Messinian salinity crisis. 1.7 million years is 4 times longer than the duration of the crisis itself. This asymmetry is striking. The destruction of biodiversity took 400,000 years, but the recovery took 1.7 million years. This is a common pattern in mass extinctions. Ecological collapse can be rapid, but rebuilding takes much longer because it depends on evolutionary processes, dispersal, and the gradual development of complex interactions between species. The recovery was not simply a return to the pre-crisis state. Evolution had continued during the crisis, and during the recovery period. The species that recolonized the Mediterranean were not identical to those that had existed before. Some pre-crisis species had survived in refugia outside the basin and returned, but they may have undergone genetic changes during their isolation. Other species were new, having evolved in the Atlantic or elsewhere, and then dispersed into the Mediterranean. The post-crisis Mediterranean was similar to the pre-crisis Mediterranean in its broad ecological characteristics, but the details, the specific species present, their genetic diversity, their interactions, were different. The long recovery period also meant that the Mediterranean during the early Pliocene was an impoverished ecosystem compared to what it would eventually become. Productivity was lower, biodiversity was reduced, food webs were simpler. The basin functioned as a marine environment, but it was not as ecologically rich or as resilient as it had been before the crisis, or as it would become after full recovery. The Messinian salinity crisis and its aftermath illustrates several important principles in earth science and ecology. First, geological and hydrological processes can drive rapid environmental changes that cause mass extinctions. Second, the recovery from such extinctions is slow, requiring time for species to evolve, disperse, and establish stable populations. Third, ecosystems are not static. They can exist in multiple states, and transitions between states can be abrupt, driven by the crossing of thresholds. Fourth, the history of life on Earth is punctuated by crises and recoveries, and understanding these events helps us appreciate the resilience and fragility of life. Today, the Mediterranean shows no obvious signs of the crisis that nearly destroyed it nearly 6 million years ago. The sea is filled with water, marine life thrives, the salt deposits lie buried beneath hundreds of meters of younger sediments, invisible except to geophysical surveys and drilling. The canyons carved by rivers during the drawdown are submerged, their walls now clothed in marine sediments. The land bridges that connected continents are gone, submerged beneath hundreds of meters of water. But the traces remain, encoded in rock preserved in fossils, written in the structure of the seafloor. The Messinian salinity crisis is a reminder that the landscapes we see today are not permanent. They are products of processes operating over deep time, shaped by forces we can measure but can barely imagine experiencing. Seas can disappear, continents can reconnect, salt can accumulate in layers a kilometer thick, and after 400,000 years of isolation and evaporation, an ocean can return in a flood that lasts less than 2 years. The story of the Mediterranean is the story of change, of thresholds crossed, of patience and violence, of extinction and slow recovery. It is a story written in salt and silence, and in the roar of water reclaiming an empty basin.